5G is not ready up to fulfill in all terms. So maybe it's also part of it is maybe also to create or realize what we just not in our use cases could do. However, it's very, very difficult to answer the use case question, which is commercially also successful, everybody will buy. Because what we see is that we divert into something. I mean, it was single use cases in the past over the last generation. It was really the voice, it was a data, that makes systems really successful because it was just the same type of service all over. Already with 5G, we see this diversification into different use cases. For industrial, it's totally different than for a user like a broadband and an end user on your smartphone. And it will be many other users now that adopting the technology. So we see that diversification, but we want to have the same technology solving that issue. Maybe with these now clever methods of AI and machine learning that allow us to adapt to certain conditions much easier than it was possible in the past. So the real clear use case, I'm not sure about either, to be honest. But we see it's going there. It was always going forward, and I'm sure we'll have that.
If you allow me another question, maybe.
Yes, of course.
Sure.
And in terms of timeline, if we look at what happened with the former generations, like 4G, 3G, 4G, we've seen that every 10 years we're coming up with a new generation. But between the two generations, there are several upgrades. So are we gonna see the same thing happening with 5G? We'll see some upgrades within the next years, and then something like 2030 will have the first implementation and rollout of the 6G.
Yeah, as I tried to explain, I guess we will still have a little bit of course of evolution in 5G because that system has just been realized out in the field, and I'm sure people will add on. As I mentioned, things like the optimization for integration in industrial applications. I mentioned non-terrestrial networks, which is quite new in release 17 now. I believe there will be a release 18 and 19 as well. However, I also think it's a little bit accelerating in terms of the next generation coming up. At least that is my personal impression right now. So witnessing now over, I think I was present in 2G and now up to 6G, it was this 10-year cycle, as you mentioned. But I feel for 6G is a little bit of acceleration coming up now. Although many people still say that in terms of really commercial deployments taking place, this is going to be maybe 2030. But at least from the research activities I detect, it is quite early adoption of much more concrete projects, to my understanding, that we had in the past. So maybe we see a little bit of acceleration, maybe an overlap of where really when the new generation starts and where is the evolution of 5G over. Maybe also that is with all the software power we have in contrast to earlier generation where it was still a little bit of hardware related. Now we have so much moved into the software arena that we have also maybe not a really strict cut of saying now it's a new date, right? Maybe it's also parts of a new generation which are already adopted by an earlier generation.
Thank you.
Thank you, Professor Saidi. Thank you. So thank you again, Mr. Make Goodcamp, for all the great information sharing with us today. And I will be more than happy if we could get in touch to develop partnership together with Moroccan institution and university. Thank you so much.
More than open. Thank you for having me.
Thank you, Mike. Take care. Take care. Bye.
Bye.
Mike, for this wonderful presentation.
Thank you.
Thank you.
Hafid, you can stay with us. Good morning, Professor Wiji.
Hi, good morning.
How are you doing?
Fine. I can always hear you with a low volume.
So you can hear me well or not? Okay. Good morning. Hi.
Good morning to everybody.
Good morning.
Good morning.
Good morning, Luigi.
Professor Mohammed, we can start the student presentation, or we can wait for Yarman to join us.
I think we could start. I think we could just proceed with the program. You can join at any moment. Okay.
Okay. So I don't think if Yildiz is with us. So Yildiz is with us. Professor Zas, you can give the line to Serkan Yildiz from the attendees list. Okay. Okay, so waiting for Serkan Yildiz, he asked me to wait for 10 minutes. We will start by two recorded presentation. The first one is given by Suhail Nouri and Amir Riza Khadimi, Aval, and Professor Samir Ghazali. It's about wave propagation effect on cutoff frequency of multi-finger giant met. Okay, so I will share with you the presentation. Okay, so okay. Do you see my screen?
Yes, it's coming.
Okay.
Hello, everyone. Thank you for attending this presentation. This is Sohail Nouri.
It is fine.
I think that the volume is so low, so.
The presentation title is Wave-Propagation Effects on Cutoff Frequency of
Excuse me, to solve the problem of sound, we will stop sharing for a few seconds.
Hello, everyone. Thank you for attending this presentation. This is Sohail Nouri, a PhD candidate in University of Arkansas. I'm with the Department of Electrical Engineering in Dr. Al-Ghazali's research group. The presentation title is Wave Propagation Effects on Cutoff Frequency of Multi-Finger Gallium Nitride HEMTs. All right, looking at the outline, I will start with an introduction. Then I will express the challenges of current modeling methodologies. I'll talk about the wave propagation effects, and then I will introduce my proposed Wave-Electron-Transport or WET model. I'll talk about the coupled multi-conductor transmission lines a little bit, and then I'll share some simulation results with you to validate my WET model, and then I'll come up with a brief conclusion. Okay, so the development of high-frequency product begins with system architectural design, followed by RFIC, MMIC design, then integration of the ICs onto an RF board or RF module, and finally verification. And a basic requirement for the high-frequency design chain is accurate or availability of accurate simulation models. But why model quality is a leading contributor to the simulation accuracy? Because it reduces the number of design cycles, and it shortens the design time, and potentially it reduces the design cost. Let's discuss the challenges of current modeling methodologies a little bit. So the traditional parameter extraction methodologies are based on DC and RF measurements, and they are not adequate enough to describe all aspects or all physical phenomena that may impact the high-frequency design. The problem with measurement data is that they include parasitic effects of device pad and interconnects that must be de-embedded. The other thing is that several parameters are fitted to a large amount of measurement data using optimizers, and logically, the simulation results that are based on measurements are accurate only over the range of optimization. And the final point is that they do not account for physical phenomena like wave propagation effects and nonlinearities such as 1 dB compression. Now let's see what the wave propagation effects are. We all know that the device width is limited by two factors: the signal attenuation along the device electrodes and the phase velocity mismatch between the input and output electrodes. The first factor is in low frequencies, and the second factor is in high frequencies. And the second factor is even worse in millimeter wave band. But what really happens in higher frequencies? Well, the device width in millimeter wave band is a considerable fraction of wavelengths. So the waves traveling inside the device experience different impedances in input and output electrodes. So there will be a phase velocity mismatch and phase cancellations in voltages and currents along the electrodes, and this wave propagation effects degrades the performance of the device in millimeter wave band. But what is the solution? The first solution is to limit the device width to 1/10 of the wavelengths. But we all know that all researchers desire to have wider device, because wider device can provide much more power, much more output power, basically, and more gain. So the second solution is to design or come up with novel topologies to avoid the phase velocity mismatch. But before doing any design, an accurate modeling approach based on distributed effects is needed to account for the wave propagation effects and to predict the device behavior in millimeter wave band. And here's the point that I want to start presenting the Wave-Electron-Transport or WET model. All right, looking at the device structure, it's the general structure of a millimeter wave transistor. It has two parts, the extrinsic part and the intrinsic part. The intrinsic part is where we have all the epitaxial layers, the semiconductor layers, and the extrinsic part is where we have all these electrodes. For the intrinsic part, a device solver is needed to solve the electron transport equations. It's being developed, this device solver is being developed in our group by another PhD student, but right now, at this point, I'm using Silvaco Atlas simulator to come up with solutions for the electron transport equations. So the device solver solves or models the intrinsic part. Now let's look at the extrinsic part. The distributed, in millimeter wave band, the distributed approach addresses the modeling challenges by dividing the electrodes into infinite incremental pieces of conductors, and each one of these segments have the width of dz. And since in millimeter wave band, the electrodes act as multi-conductor transmission lines, the governing equations should be solved. And here is where I use FDTD solver to come up with solution for the governing equations for these coupled transmission lines. So in other words, we have two solvers in our model. The FDTD solver models the extrinsic part, or it models the wave effects. And the device solver models the intrinsic part, providing solution for the electron transport equations. And here we will need an interface code. We have developed one, and it's needed to exchange data between the solvers while our numerical method iterating. Let's talk about this coupled multi-conductor transmission lines. So 1 minute segment of device width is shown here in this figure. The first step in MTL analysis is to determine the per unit width parameters of this inductance, resistance, and the coupled capacitances. I have developed closed form equations to find capacitance for planar conductors of this transistor based on the conformal mapping technique. But here in this work, I have used COMSOL multiphysics to obtain the values for these coupled capacitances. And having the capacitances in hand, we can easily come up with the values for inductance, and using Wheeler's incremental inductance rule, we can find the resistance of the model. The second step is to terminate the end of the lines with like appropriately. To do this, we should look at this the path configurations. There are two general configurations. The first one is the fork configuration, and the second one is T-feed configuration. Looking at the pad layout, we see that end of the lines can be either open circuited or matched. And this is very important to terminate the ends of the line appropriately. And the final step is to solve the MTL governing equations. As you can see, there are two sets of equations. The first set is used to update the current along the electrodes, the line currents, ID, IG, and IS. And the second sets of equations are used to update the voltages on the line. So the drain voltage, the gate voltage, and the source voltage. All right, now let's take a look at the simulation results. Here we have a fabricated device. This device is fabricated on a silicon carbide substrate. It has a gallium nitride buffer layer, an AlGaN back barrier, followed by a gallium nitride channel, an AlGaN layer, and finally the GaN cap. The device width is 25 micron, and the number of fingers is 2. The gate length is 90 nanometer. The drain gate spacing is 600 nanometer, and the gate source spacing is 120 nanometer. The device is biased at 12 volts and 500 milliamps per millimeter. Here in this graph, we see the gain in y-axis and frequency in x-axis. There are two curves. The red one is the current gain versus frequency. The dashed curve is the measurement results, and the dots are the results from my simulation. And the blue curve is the maximum available gain. Again, the dashed line is the measurement results, and the dots are my simulation results. In order to get the current gain, the output is open circuited according to the definition of cutoff frequency, and and to obtain the maximum available gain, input and output ports are matched. As you can see, there's an excellent agreement between the measurement results and the simulation results. Now let's look at another case. Again, we have a gallium nitride HEMT device. The gate length is 0.1 micron. The device width is 25 micron, and the number of fingers is 2. The gate source spacing is 0.3 micron. The gate drain spacing is 1.6 micron, and the device is biased at 17.5 volts and 388 milliamps per millimeter. Looking at the graph, again, we have two curves. The y-axis is the current gain, and the x-axis is frequency in gigahertz. And the intersection between the curves and the x-axis shows the cutoff frequency, according to the definition of the cutoff frequency. The dashed line is the measurement results. It shows the current gain versus the frequency for a device with 25 micron width and 2 fingers. And the dots in blue are my simulation results. As you can see, there is a good agreement between the measurements and the simulation results. So here, I basically validate my modeling approach. So for a device of 25 micron, the model is validated, but I went further and I tried to predict the device behavior for a wider basically device. So looking at this purple curve, this curve is the current gain for a device of 60 micron with 2 fingers. As you can see, after this point, the current gain starts falling because of wave propagation effects. If there was no wave propagation effects, the cutoff frequency could be 42 gigahertz higher than the cutoff frequency for the case that we have wave propagation effects. So here, the VET model is capable of predicting the device behavior for a wider device at higher frequencies because it can, or it accounts for the wave propagation effects. All right, so let me wrap up the presentation with the VET model advantages. It accounts for the wave propagation effects, and it's not limited by the device width, by the frequency range, and it's not limited by nonlinearity. So in other words, it can model the device behavior either in linear or nonlinear parts. Well, of course, all of the not covered in this paper. We have published some other papers that we have studied all these advantages. And the last one is that the VET model does not rely on measurements, and it's merely based on the geometry of the device, the epitaxial layers, and the pad configurations. Right here, I would like to acknowledge the US Army Research Office to support this work, and any opinions, findings, and conclusions or recommendations expressed in this presentation are those of the authors and do not necessarily reflect those of the US Army Research Office. Thank you again for your attention. Please feel free to ask any questions.
Okay. Welcome, Professor Siddiq Yarman.
Thank you so much, Osman.
So you are the floor to chair this session, okay?
I mean, you mean
okay.
Yeah, but I'm not chairing the session, do I? No.
Okay, it's fine. So, okay,
so you guys are in charge. All right, I'm just a listener now.
Okay, so this is a resistant presentation. Now let's move to another one, which is recorded. Just 1 minute. So the presentation is given by Amir Khadimi, Reza?
Hello, everyone. This is Amir Reza Gadimianvel. I'm a PhD student at the...
It is fine, so you can hear the voice. Can you hear me? Can you hear me?
We hear you, but I don't know if the presenter hears you.
No,
Department of Electrical Engineering, University of Arkansas, Fayetteville, Arkansas.
So you can hear the presentation, no? Okay, it is fine. So it is fine. Okay, I will.
The title of our presentation today is the large signal. Hello, everyone. This is Amir Reza Gadimianvel. I'm a PhD student at the Department of Electrical Engineering, University of Arkansas, Fayetteville, Arkansas. The title of our presentation today is the large signal modeling of high-frequency gallium nitride HEMTs, including electromagnetic wave propagation effects. So the outline of the presentation, I'm going to give you some introductory materials, then I'll discuss the device structures. Then I'll talk about the wave propagation effects and will give you the details of the device modeling. Then I'll discuss the parameter extraction and will provide the distributed approach, and finally wrap up with the comparison results and the acknowledgement. Okay, so for the devices that are either working right now in the wireless communication systems or will form the future of these systems, there are a couple of features that are very important: high efficiency, high gain, high power density, and high frequency of operations are among those features. So as we all know, a promising choice is the wideband gap gallium nitride that are used mostly for fabricating devices such as high electron mobility transistors. So our promising choice as a device to work in the wireless communication systems is the gallium nitride HEMT. So now we have this device as an important element, and we want to improve the device performance. So it demands, of course, a developing modeling technique. So a tool that we can have in hand, so that based on that, we can optimize our device, we can improve the device design, and so forth. In this presentation, our main focus is on equivalent circuit models. So equivalent circuit models, this is not something new. It has been around for many years. And of course, there are limitations with these models. And one of the two of the main limitations with these equivalent circuit models is, number one, the high frequency unreliability. It means that the model is actually reliable up to a frequency range. When the frequency range or the operating frequency increases that range, or the device operates at an upper frequency band, what happens is that the model is not reliable anymore. We need to probably add some more elements in order to account for some physical behaviors that are happening at the upper frequency range. So we call this a high frequency unreliability. And number two is the measurement-based procedures. What it means is that in order to have an equivalent circuit model, the device is first fabricated. Then using the measurement and experimental results, we basically come up with a model as a tool that basically can be used for simulating that specific device. But it just doesn't make sense. The simulation tool is something that we want to have it beforehand the fabrication and design process. So if we want to have it after that, it just doesn't make sense. So we will try to come up with solutions for these two problems. So in this presentation, an important phenomenon that needs to be considered in high-frequency devices, and we will be talking about that, is the electromagnetic wave propagation effects. This will be considered in two different categories: the device fabrication and, of course, the circuit model development that we will explain more in this presentation. All right. Let's look at the device structure. This is the device that we have used all over this paper and all over this presentation in order to develop our model. This is an AlGaN-GaN hemp device. Regarding the main characteristics of these devices, first of all, it is fabricated in the University of California in Santa Barbara by Dr. Mishra's research group. The device is grown by the metal organic chemical vapor deposition on an A-plane sapphire substrate. Then the next semiconductor layer is the semi-insulating GaN buffer, a silicon dope AlGaN as the back barrier. We have another AlGaN layer as the interlayer. Finally, the gallium nitride channel, the unintentionally doped one, and on top of that, there is an AlGaN cap. But the most important probably feature that we want to focus here is the trapezoidal gate structure. So with the previous devices, with the traditional, say, hemp devices, there was a huge problem, which was the resistance on the gate electrode. As the signal moves from the starting point to the end of the device through the width of it, there was actually a degradation of the signal or an attenuation of the signal because of the gate resistance. Now, with this specific structure, the trapezoidal gate structure, we can make sure that we have enough cross-section for the gate electrode so that that resistance reduces to a value that we can make sure that the signal will not degrade at least that much through the device. Okay, after we know about the device structure, let's go to the wave propagation effects, really the gist of this presentation and what we want to basically focus on. So, as we already discussed, for the wireless communication systems, or basically the systems that we are interested in, the operating frequency is in the range of microwave and millimeter wave. So, based on this fact, we know that the wavelength inside the device not only large, but to the other systems that are, of course, working at a lower frequency band. So, first of all, what we need to emphasize here is that we need to make sure that when we are working at these frequency bands, specifically microwave and millimeter wave, we need to make sure that the concept of wave is also considered inside the device, or the concept of wave propagation. All right, now with this lambda, that for these devices is notably large compared to the other devices and systems at the lower frequency bands, the device width becomes comparable to lambda. So what is the device width? This is actually the dimension that most of the time with the 2D transistor cross-section figures, we do not see. It is actually the dimension along the electrodes of the device, or basically the dimension that is perpendicular to the electron flow. So this width that most of the time, not most of the time, I would say all the time, is the longest dimension of the transistor, is actually something that becomes comparable to lambda in these frequency bands. So what happens is that since the input and output impedances are different, this is something innate to the transistor itself, the signals will exhibit different phase velocities. The signal on the gate and drain electrode, the signal at the input and output conductors will have different phase velocities. So what happens is that in this case, we say that wave propagation affects the electrical behavior of the device. So now the signal on the gate electrode and the signal on the drain electrode will have different phase velocities. They will have some effect or some impact on each other continuously throughout the signal or the wave traveling through the device width. So continuously, the gate will have an effect on the drain, and the drain will have an effect on the gate, and this will just continue all along the device. And this is when we say that we have an effect, we have the wave propagation effects on the electrical behavior of the device. So, and in most of the cases, of course, this effect is actually a degradation. We do not see the gain that we want at the device output. We do not see the power that we want at the device output. And this is how the device is not actually a high performance one at a specific frequency. Or let's say when, for example, the device is not working at a specific frequency, then above that frequency range, the device will also be useless as well. All right. So in order to avoid this phase cancellation, of course, we need to look into it in two ways. Number one is the fabrication methodologies. So traditionally, in order to have a solution for this problem, what happens is that they just try to minimize the device width. They just try to keep it at very, very small values compared to lambda. For example, somewhere around lambda over 10 to lambda over 20. And that's how they can avoid this problem. They will no longer have phase velocity mismatch. But the problem is that when you keep the device width really small, you're just losing a lot of things. You're losing for the gain, you're losing the output power that you can get with a wider device, let's say. So right now, I mean, with the current research that is being done on this specific topic, novel fabrication methodologies are utilized in order to basically relax this limitation, and this is something that we are currently working on. But in this presentation, we are focusing on the modeling. So the wave propagation effects needs to be considered in the modeling as well, and this is how we come up with the distributed approaches. So we are going to use a distributed equivalent circuit model in here, which we say that is actually a universal equivalent circuit because it will be reliable over a very, very broad frequency range. So let's see how we are doing it. All right. So this is the 16-element equivalent circuit model, as we can see in this figure. The passive section is a section that we have the bias-independent elements, the elements that are related to the electrodes, their configuration, and anything that is not related to the innate of the transistor itself. And of course, the active section, vice versa, is the bias-dependent elements, the elements that actually are extracted based on the innate behavior and the operation of the transistor itself. Regarding the extraction procedure for these elements that we have over here, first of all, we need to say that this is based on the physical layout. So since we do not use any type of experimental results or measurement results, it is something that we can make sure that this modeling thing is available beforehand the fabrication. So this is based on the physical layout of the structure. We start with finding the capacitance. Of course, for that, we start with the passive section. For finding the capacitance, we use a conformal mapping. So we have these conductor planes, and we try to use the conformal mapping in order to find the capacitance between these conductor planes. Then finding the inductance is just simple based on the quasi-TEM approximation that we have an assumption. We have as an assumption in this basically frequency band that we are working in. L will be just simply equal to mu epsilon over C, the capacitance that we have already obtained. For finding the resistance, we use the already well-developed Wheeler's incremental inductance rule. And now that we are done with the passive section, for the active section, we use Silvaco simulation tool. We just simply use the 2D transistor configuration in the Silvaco, and then after basically trying to simulate this device in Silvaco. We get the Y parameters, we extract the Y parameters, and using those Y parameters, we just come up with the values for all the elements that we have in the active section. Okay, but this is not the end of the story. Here is basically the most important part in the approach or in the modeling process. This is what we call the distributed approach. So we say that in order to incorporate the wave propagation effects, first of all, we say that we divide the device width to n sections. Each of these sections, which we call a unit cell from now on, will have a width of delta z. So to incorporate the effects, we need to make sure that this delta z is kept much, much smaller than lambda, somewhere around lambda 10, lambda 20, somewhere between these. So with this set, what happens is that we will have a configuration, just like what we have in this figure below. This is the configuration of the distributed model that is representative of the whole device width. Now, each of these unit cells will have a configuration of the model just like this, as you can see here. And finally, we will have this model as the distributed model that can be used over a very broad frequency band. So the boundary conditions are applied based on the figure on the right side. As you can see, we have the boundary conditions from the top view schematic. They also will be applied in the distributed model. And finally, it's just some equations, some coupled equations for finding the voltages and currents over all the nodes and lines. So since we do not have an analytical solution for these specific equations, we will use a numerical method, which we use in here. We use the FTDT for the analysis. So now let's look at the results now. Okay, so here is the comparison results. This is for the small signal case. We start with the small signal case first. The gate length for the device that we just introduced is 0.1 micrometer. The gate source spacing is 0.2 micrometer and gate drain spacing is 1 micrometer. The operating frequency that we have the measurement results for is from 0.25 to 67 gigahertz. For this specific case, we're using 5 unit cells. So as we explained here, we need to adjust the values of n and delta z in order to make sure that for the operating frequency of the device that we are looking into, we are totally safe and also make sure that the wave propagation effects are included. So in this specific case, since our basically highest frequency is 67 gigahertz, having n equal to 5 is totally fine. We are on the safe side. As you can see, the figure on the left is a device A with a width of 2 times 50 micrometer. The only thing that is different between the devices is the width of the device. The VDS is 5.5, VGS is negative 4.6 volts. And as you can see, the solid black one is the measurement results. The dashed red one is the distributed model. And we are getting a pretty good agreement for the current gain in dB versus the frequency from 0.25 to 67 gigahertz. The figure on the right side is device B, again for that frequency range, and we are looking at the current gain once again. Device B has a width of 2 times 25 micrometer, and 2 times basically means that we are using 2 finger in a T configuration, as we saw here in the top view schematic. And at a VDS of 11 volts and BGS of negative 4.8, we are getting, again, I would say, an excellent agreement between the measurements and simulation results. So we are totally fine with the small signal case. We also went ahead with the large signal simulation as well. In this case, we are using, again, the same configuration, but for a device width of 2 times 75 micrometer. This device is operating under class AB at a frequency of 10 gigahertz. The IDQ for this case is 100 milliamps over millimeter, and VDSQ is 20 volts. So as you can see, we are looking at 2 parameters here. The figure on the left is P out in watt over millimeter versus P in dBm. And as you can see, once again, the measurement and distributed model or the simulation results are having pretty good agreement. And also for the figure on the right side, you're looking at the gain in dB versus Pn in dBm. And once again, as you can see, we are having excellent agreement between these two results. So we developed a model in this work and we presented it in this basically work that is able to simulate the device over a very large or broad frequency of operation. And also the large signal simulation case showed that it can also be extended to give us the values for the nonlinear operation and nonlinear results as well. And also we want to acknowledge the U.S. Army Research Office for supporting this work and research. And also wanted to say that any opinions, findings, conclusions, or recommendations expressed in this presentation are those of the authors and do not necessarily reflect those of the U.S. Army Research Office. Thank you so much for listening to this presentation.
Evet.
Good morning, Gupta.
Morning.
How are you doing?
Morning.
Benim öğrencim.
Morning, everybody.
Well, welcome, Gupta. Hello, nice to see you.
Hello, everybody.
Söylemedi bana bas. Hayır. Söyle.
Hello. Is this Serkan still now?
Yeah. Serkan?
Yes, I am here.
Okay, you can start presenting your work.
Okay. Well, how can I share my screen?
Look at the green button.
All right.
Okay, so
Bassam'ın yayını yoktur bildiğim kadarıyla. Yani benim bildiğim bir yayını bir şey yok. Olsa benim zaten bilmem lazım.
Typhoon, you can turn off your mic.
Share screen.
Okay.
Okay. Tamam. Değil tabii de.
It's not active. This screen sharing is not active in my desktop.
Okay.
Yeah.
Just give me.
I think you
maybe
can
you
make
should
him
meselesi Mustafa'nın
Give me just 1 minute.
Aşırttı onu. Evet. Tabii.
Yıldız, can you
yukarıdan birileri bunu attığı paspasın altına bir süpürme mekanizması var.
Timur, please. Timur.
Tepede bir şey var sırtında arkasında.
Is it okay?
Yeah, it is okay, but we need to.
Yeah, Typhoon, can you hear me? Hello, Typhoon. Typhoon, can you hear me?
Can you turn off your mic, please?
Okay.
Okay. So, Professor.
Can I start?
Okay, we can wait for Professor Gupta.
Konuştuk o meseleleri, böyle briefly konuştuk yani. Yani Ali'yi çok takdir etmek lazım ve takdir de ederim zaten. Yani hepimiz dedik bravo yani. Çığırından çıktı, olmaz. Kulak çekme. İşlemiyor buna kulak çekme. Adam
So, Yildiz, you can start your presentation.
Okay, thank you very much. My name is Serkan Yıldız. Today, I work in the Technological and Scientific Institute of Turkey, TÜBİTAK. And today I will present a triple band filter design method that is based on frequency mapping technique. This is a part of my PhD study. I will give a brief introduction about why we need such a mapping functions, and then I will present my our novel triple band mapping function, and then there will be a application of this method. So let me briefly give a brief introduction. Multi-band filters are essential components in all RF and microwave units since the development of the technology and the new telecommunication protocols are coming up. So we need multi-band filters. So an equipment and a single unit can be able to give service all these protocols, such as a mobile phone. It should support GPS, GSM 900, 4G, 5G, all same time. So multi-band filters are extensively investigated in the literature. So the main these filters have many beneficent, such as they improve SNR, they suppress the interference with adjacent bands. In comparing with the ultra-wideband systems, multi-band systems have more improvement in RF parameters. So the ultimate goal is as shown in the figure. So we want to create pass bands in our assigned cutoff frequencies, and we want this band as much as possible according to our application. This is the main goal. Several approaches have been published in literature. Some of them use MEMS switches, but MEMS switches it requires a driver circuitry, and it is more complicated, and also concurrent operations may not be possible in this way. Also, some other tracks are available in the literature, such as distributed elements, distributed circuitry are used in several publications. But a generalized method in analytical method can be produced, can be generated either by using frequency transformations or driver impedance, or based on the driver impedance definitions. So in this paper, we took the first one. So we choose a frequency transformation method to generate a triple band filters. So in these methods, low pass to band pass transformation, the well-known low pass to band pass transformation is applied on a prototype network. It is generally a low pass network, and the band pass characteristic is produced. So if we keep applying the low pass to band pass transformation, the even ordered pass bands occurs. For example, if we apply once the low pass to band pass transformation on the low pass filter, we have a single band pass filter. If we keep applying one time, then dual band filter will occur. If we apply this transformation, the same transformation, low pass to band pass transformation on the dual band filter, then we have a quarter band filter. So there is not in literature, there is since now there is not a way to produce a sequential transformation scheme to get a triple band, a odd ordered triple band filter. So in one of our previous research, we have published a very useful method, a very useful transformation function that we can generate a dual band filter in a single step. So this function is also based on the low pass band pass transformation. But besides of using in 3 sequential steps, we just jump to 1 step to get the dual band transformation. Also, one of our other previous research, we also give the quadruple band transformation. This is also a single step. But we want to use the same low pass to band pass transformation to produce a triple band filter, but it seems it's not possible. So we dig into our research, and in this paper we present our transformation function, and we apply this transformation function to generate a triple band filter for GSM 900, GPS, and LTE bands. So in this paper, we present a triple band function, and we also give a microstrip application, the simulation results for the microstrip applications. So let's start. So here is the ultimate goal, as I said. So we take a low pass filter, and we produce a triple band filter, and we want to make it in a single step. So at the left you see the transformation scheme, and at the right you see the mapping diagram. So the mapping diagram maps the low pass characteristic to triple band characteristic. So here is our low pass to triple band transformation. We derive it. So we make it more after some mathematical modifications. We make some simplifications in the equation. So here is the final form in 3, and we should and in the relation in 4, it says the whole cutoff frequency, the symmetrical cutoff frequency should have geometrically there should be a geometrically distributed around the central frequency omega 0.3. So also the relation between cutoff frequency should be kept. So the omega 1 smaller than omega 3 and smaller than omega 3, etc. So this is also obvious since the first cutoff will be lower than second cutoff and lower than third cutoff. So so to find the coefficients of this equation in 3, we set according to this mapping diagram. We see that in this mapping diagram the omega absolute value of the omega should be 1 at the cutoff frequencies. So we solved this equation, and we found the coefficients, and we built our transformation according to our specific application. So in the application, we try to we have presented this filter. This filter is cover GSM 900, GPS, and GSM 1800 bands. So the cutoff frequencies of the triple band mapping functions are chosen as 0.85 gigahertz to 1.1 gigahertz, and the second band is 1.4 gigahertz to 1.7 gigahertz, and the last band is 1.16 gigahertz to 1.8 gigahertz. So so after we define these cutoff frequencies and we use the formulations and we found the unknowns of the equations in 6. So now we have our transformation for our application. Then we choose a low-pass prototype network. This network can be any well-known low-pass network such as elliptical, Bessel, or Chebyshev. Here we choose Chebyshev elliptical filter. It's fifth degree Chebyshev elliptical filter. Chebyshev filter, low-pass filter. So we apply this transformation on the element of this filter. So for the element transformation, so each inductance in the low-pass network is mapped to this resonance section in A. So the element values are also element values of the figure also generated by using these above equations. So each capacitance, each capacitance of this network is also set by error. So each capacitance of the network is also transformed in the resonance section B, and elements values are calculated. So here are our triple band filter. So it is derived. So we apply this transformation on this low-pass prototype network, and we get our triple band filter here. At the table, you see the element values. This is the characteristic of the filter. As you see, the bands, the defined cutoff bands are satisfied. So this is the AWR and analytical results. So after this, this topology is an ideal topology, lump element topology. If you want to make an application, so we need to transform some of the lump elements to their distributed correspondences. So we made Fourier transformation function, which is defined according to design according to the user entries. So after we define our cutoff frequencies, we get our mapping function, and if we apply this mapping function on a low pass filter, then we get our triple band filter. So for this application, we made our filter to pass the GSM 900, GPS, and UMTS bands. These bands are covered. So these are my references. So thank you very much for your for this opportunity. And if you have any question, I will be happy to answer.
Okay, thank you, Yildiz, for this presentation. Now let's pick up some questions we have. I think Professor Gupta, you have one. You can activate your mic. We can't hear you, Professor Gupta. You can activate your mic, please.
Am I audible now?
Yeah.
Yes.
Okay. Let's see there. Most of the time I also could not hear anything, so you better ask questions. I'll join later. I am here listening to the presentation, but right now no question, please.
Okay, I think I have one. Can you explain what is the novelty of this work in comparison with?
Yes, of course. In this work, first of all, in literature, there is not a sequential transformation scheme to get a triple band filter. So we use a very simple formula, which is low pass to band pass transformation, and we get the triple band filter. So according to if we keep applying this transformation on and on, so normally we get a quadruple band filter in the third step, but we get in our work represent that it's possible to get a triple band filter with this. Also, besides of that, our transformation function is user defined. So it's possible to define the cutoff frequencies. Also, it gives a very a very practical tool. In literature, there are many other methods, but they are very complex, and they are for special topologies such as distributed structure and comb-line filters and 3D filters. But these methods gives a design methodology, and you can get a low pass and a lumped filter, a lumped triple band filter, and of course you can transform this filter, transform this lump topology to distributed topology as well, or to other network realizations. So in our latest one of the latest publication in radio engineering, we generalized this method for nth band, for arbitrary bands. So you can use this method, and you can generate a multi-band filter with this method. We also published this paper in the radio engineering journal. Here is the reference. So thank you for the question.
Okay, thanks, Yildiz. Do you have other questions?
So is there anything new which has not been reported in that radio engineering paper? Did you report anything here? Not there in radio engineering paper?
Well, this in the radio engineering paper, we use a generalized form.
Yes.
But here we only use the triple band form. Also in the radio engineering paper, we solve this equation by we solve only the coefficients of the equations. But here we solve the parameters of B2 and BS2 factors. So here we in the radio engineering paper we give it a generalized form, and here we only represent the triple band form. But also here here the equations that we represent. We solve this equation to generate the design parameters, which are the B2, BS2, and omega 02, which are the which are used to define the second dual band characteristic of the second step of the transformation here.
Do you think there's any limitation of this technique? It's a based on simple transformation. So any limitation of this?
Well,
any
of
limitation
course,
of this technique?
There is a limitation. The relation between the cutoff frequencies is so we can assign only the fourth cutoff frequency since the geometrical the cutoff frequency must be distributed around around the center frequency, geometrically distributed around the center frequency. So we are allowed to determine only four cutoff, or for any four cutoff frequencies. So we can, if we determine, if we choose omega 1, omega 3, omega 4, and omega 3 and omega 4, then omega 5 and omega 6 are generated according to geometrical mean formula. So this is also since our equation is based on the low pass to band pass transformation. In low pass to band pass transformation, the geometrical means also must be satisfied. So the between the cutoff frequencies omega 1 and omega 2, there should be a geometrical mean, the center frequency of the pass band. So in our formulation, this since our method is based on the low pass to band pass transformation function, so in triple band form of this function, the geometrical mean rule also applied. So this is the main one of the main restriction. So according to application, we are free to choose any four cutoff frequency. Then we need to make free the last two cutoff.
Okay, David. Is there any other question?
Okay, if not, we can move to the next presentation.
Yes.
Okay, so the next one is given by Malik Ihsan Ijaz. Okay, Ihsan.
Thank you very much.
Malik, you are with us?
Yes, good morning, everyone.
Okay. So you
I'll
can
try
share.
to. So can you guys see my screen?
Not yet. Now I think it's okay.
Okay, all right.
Okay.
So my name is Malik Ehsan Ijaz. I'm a PhD student at University of Lincoln with Dr. Saket Srivastava and Dr. Siddiq Yarman. The presentation that I'm going to do today, it's on 10 watt GaN PA for 5G NR N78 band, utilizing RF parametric approach, real frequency synthesis parametric approach. So today's agenda is that we'll just have a quick look, a scan through the 5G requirements for SSPAs, then go into device technology selection, that how did we come to the selection of the technology. We'll go through amplifier design, steps that we have taken, finally conclusion and question and answers. So this is in a quick glance that's been taken from a paper published by Nokia. You can say that there are kind of two bands, FR1, FR2, sub-6 and into 24 gigahertz bands. The main thing to notice here from previous generations is that the channel bandwidths are going to be pretty wide for 5G. For sub-6, the current deployment is at 100 megahertz, but they're looking into the next section to take it to 200 megahertz. And it's more wider when you go into 24 to 28 gigahertz band. So it's about 1 gigahertz. So that puts pressure on power amplifiers to be a bit more broadband in terms of bandwidth. But also, if you look at the Cat B emission limits for FR1, you have minus 36 dBm at 1 kilohertz, 10 kilohertz, 100 kilohertz away from the carrier, and minus 30 dBm at 1 megahertz. So if you're looking into in terms of a 10 watt amplifier with a peak of 10 watt, then that's about 76 dBc or 70 dBc rejection of unwanted signals, and that's pretty stringent. And it puts a lot of pressure if you have to achieve such a wide band amplifier, and also have to include some level of efficiency, and then on top of that you have linearity. That's again, this is another factor which we call peak to average ratio. So for DFTS, OFDM type of multiplexing waveforms, it will be about 8 or just above 8 dB of peak to average ratio for 5Gs, and that's even with the crest factor reduction. So that puts another pressure that on the efficiency side of the amplifier, that if you have to operate an amplifier with 40 dBm of peak power and 8 dB of peak to average ratio, then maintaining, let's say, 60 or 70% of efficiency at peak, and with the 8 dB backed off, you will not get that. However, there will be compromises, and that's where we will be looking into. In terms of device technology selection and also power amplifier specifications, for any power amplifier, the main factors that we usually look into is that what sort of power we need, what sort of bandwidth we require. Gain, obviously, it's a factor that which plays a part in efficiency. Then we look into efficiency and linearity. So for our design, obviously we couldn't go for all of these factors, or we could not just in one go tackle all of it. So we went for bandwidth, power, efficiency, and gain. Looking at the parameters that we defined at the point of design, we wanted to have obviously an amplifier which covers N78 band, which is 3.3 to 3.8 gigahertz. With a minimum gain of 13, if we could get more, then that would have been nice. Output power, we are talking about peak power here, 40 dBm. Efficiency, minimum of 60, and that again at the peak power. And gain flatness, if we could get plus minus 2 or even better. In terms of VDD, looking at the devices that are available in commercially in repeaters for 4G LTE, and also in some of the communication jammers which require linear amplifiers, 28 to 32 volt is kind of the figure that is the pretty much industry standard. However, there are devices that operate at 48 and 50 volt as well. In terms of device technology selection, if we compare silicon gas, silicon carbide, and GaN, I think there are a few factors that are important to note here is band gap energy. So GaN has 3.4, which allows us to work on high voltages. The breakdown voltage is pretty high on GaN, which is very important in terms of efficiency, because if you have a high voltage, then you can draw less current, and it helps to improve your impedance value. Since thermal conductivity, or in all, that's another factor. Silicon carbide has a pretty good thermal conductivity, which we must admit, and that's why I think usually GaN over silicon carbide is used, and that's what we will be selecting for our device as well. Relative permittivity of 8.9 is also a good factor in GaN, because if you have a device which has low relative permittivity and high watts per millimeter, which GaN has, then you can have a small device, and small device means that your output capacitance is going to be less, and you can achieve a broader band response. And that's why GaN devices, for two factors, that one, they provide a lower output capacitance and they provide high output impedances, are very good candidate for broadband amplifiers. And that's why we selected GaN as a technology for our design. In terms of power amplifier design steps, the following steps have been taken, and we will go through each of them through the presentation. So IV curve extraction is required, so we can select the operation class of amplifier. Stability analysis, just to see if the transistor that we picked up is stable in the band that we are operating, and to some extent out of band as well. Source and load pull has been performed to extract the input and output impedances, and input matching and output matching network extraction has been done using RFT, real frequency synthesis, parametric approach, and then the lumped element extracted from RFT are transformed to microstrips. Finally, we included bias networks, fine-tuned the amplifier, and presents the result. And at the end, we will present the layout for the fabrication. So this briefly, this is the IV curve setup in Microwave Office, that the design tool that we have used for this design. And looking at the IV curves, you can see that point that we have chosen, it's kind of in class AB of this amplifier. I wouldn't call it deep class AB, but it's somewhere between deep class AB and class AB. So it's a best compromise for efficiency and linearity going forward. So stability analysis, K factor, Rowlett factor that we call, this is a transistor without any application of stability networks around it, which produce or present some level of losses, real losses. As it is, without any real losses on the input or output of the transistor, it looks pretty good. And especially we need to understand that when we apply input-output networks, the copper losses also contribute towards that. So the figure of 0.7 and 0.9 are not very bad to start with for this design. And in personal experience, I mean, it's good figure to start with. I would have been worried if it was 0.1 or 0.2, then I would have included some level of resistance or real losses to bring it up to about 0.9, 0.7 before I could start the design. In terms of source and load pull concepts, it's very important to understand that what we are looking for here. So the middle is device under test, or the transistor. So Z of S is the impedance that we want to present on the input of the amplifier or the transistor to extract as much as possible gain. So since the input side of the transistor usually controls the gain, output side, we want to present Z of L. And Z of L is the impedance that we want to present to the transistor on its output to extract as much as power and obviously the good efficiency. And that's what we will be doing going forward. So this is the setup in microwave office that we have set up and to extract the input and output impedances of this transistor. And these are the values that we extracted at 8 frequency points. So input impedances, as you can see, is pretty good, nice and even spread. And the transformation from 3.2 to 3.9, you can see that there's not a huge change, which is a good thing. Same on the RL side, you can see that 14 going down to 12, it's not a bad figure. And efficiency wise, we can see that at least on single frequency points, and it's important to understand that these are the single frequency point figures, it's pretty good. And gain also is very good at single frequency points. Then we move on to a real frequency synthesis technique, which is developed by Dr. Yarman, and the algorithms are in MATLAB. So we utilize MATLAB algorithms for that. So for that, if we say that let Z of n, j omega, which is a function of frequency, looking at the figure down bottom here, is the optimum termination that we want to present, and Z of n being the load pulled value that we have in the previous table for the input port of our transistor TR over the measured frequency, then we can also say that Z of C, which is a computed function, be a realizable model for the optimum impedance Z of n. Now, what is the difference between Z of n and Z of C? We'll see in a minute. So based on the above description, we can call that Z of C is equals to A of P and B of P. A of P and B of P are polynomials. And Z of C is a computed driving point impedance function, which we will drive utilizing Z of n, the load pull data. And that's the relationship between the two. It's also important to understand that ZTRN, which is the input impedance of the transistor, is equals to conjugate of Z of n for maximum power transfer. And if we keep that in mind, the perfect impedance model of Z of C j omega for Z of n all will yield TPG of unity, and TPG is transducer power gain. So the formula for TPG is equals to power to load over power from amplifier is equals to 4 RC/Rn, and it kind of makes sense if we, for the sake of argument, if we set R of C equals to 1, R of N equals to 1, then we'll see that R of C times R of N, the top will become 4, and the bottom, this part will also become 4, since 1 plus 1 is 2 and square is 4. And X of C and X of N will cancel out each other for maximum power transfer, and that will be 1. However, in real life, we don't get TPG of 1. We set an algorithm somewhere about 0.9 to 0.95. So using RFT parametric algorithm, the driving point impedances functions, coefficients or polynomials have been calculated, and these are the values for those, which will be utilized obviously to synthesize the network. So in this case, the driving point impedance functions, once that's been established, it's been fed to Darlington synthesis algorithm, and this is the network for the input side that we have extracted. And the quality of network can be seen here. So this plot here is not the gain plot, but in fact the insertion loss plot of the network. And we can see that it's pretty flat across the band of operation. Similarly, on the output side, we have performed the very same method or operation. But on the output side, now Z of TR out and Z of C again is for the output network. And the TPG is exactly the same, but this time around, we have R of out on the output side of the impedance, and Z of R of C is calculated for Z of out. Again, utilizing RFT parametric algorithm, and we have calculated the coefficients of the polynomials, which are these, and they define our driving point impedance function. And that driving point impedance function, we have fed into Darlington synthesis to get our output matching network. And that's the quality of the network. And as we can see, it's pretty straight, and the insertion loss is not very high. So this was slightly this was slightly tricky for myself to do. I used Microwave Office and these equations in the Microwave Office equation section to kind of curve fit the values of our lumped elements to microstrip. It was a slightly analytical and laborious method, but however, at the end, with some fine tuning, we did manage to get the sections of inductance and the capacitance that match with our lumped elements. And for that, we used the substrate from Rogers RO4350B, which is pretty good substrate for high frequency circuits. And these are the values for the substrate that are utilized in these equations to find the values of capacitance and inductance in microstrip. So these are input and output matching networks produced in microstrips with some fine tuning, obviously in Microwave Office. And at the end, we included the biased networks. And again, we had to perform some level of fine tuning for the inclusion of biased networks. It was intended that the biased networks don't load our input and output matching networks, because otherwise it would have been a complete retune of the input and output matching networks. So these biased networks, or biased Ts, that as we call them, they are not heavily loading our input and output matching networks. However, a fine tuning was needed. So at the end, these are our simulated results. As we know that we wanted to we wanted an amplifier between 3.3 and 3.8 with gain of minimum 13. So we can see that our gain across the band of operation is minimum 13. In fact, if anything, it's going to about 15 dB. Our power is minimum 40 dBm across the band of operation, which was required, and that's what we achieved. Our requirement was minimum 60. So in some cases, we are getting 63%, but between 3.3 to 3.8, we are at minimum 60% efficient. That's our layout for fabrication of our amplifier, which we still have to fabricate. And once we fabricate it, we will have some measured results for this as well. So in conclusion, I think it's the conclusion that we draw is that RFT parametric approach, along with microstrip theory, can produce broadband matching networks with high efficiency performance. So I think one thing that is important to understand in this, that we have gone for broadband and efficiency performance of amplifiers, and to achieve that, we did manage to get 60% efficiency. We did manage to get 10 watts across the band, and the gain was pretty good, 13 dB over the band of operation, and we did achieve that. And also, we did prove that GaN technology is a good candidate for broadband and high efficiency power amplifier designs. However, one thing that is still outstanding, and once the amplifier is fabricated, we are planning to test that and prove, and possibility that results will be shared, is the linearity performance. So this amplifier on its own cannot fulfill the requirements for 5G. It will require some sort of an external linearity improvement technique, such as analog or digital pre-distortion. And we are working on that, and possibility is we'll go for the digital pre-distortion, digitally pre-distorted amplifier, and see its performance. So this design, when used with linearity improvement technology, it will completely fulfill the 5G NR78 band linearity requirements as well. So that's it for me in a nutshell. If you have any questions, I'm open to answer.
Okay, thank you, Malik, for this presentation. Now let's move to the question section. So anyone have some questions?
By the way, in near future, when 5G and everything is launched, do you see GaN devices replacing all others, like gallium arsenide and all those things?
Okay, so I think the problem that we have to face in 5G, because I have an experience of working on GaAs and LDMOS.
Yes.
LDMOS and GaAs, in terms of linearity, they're pretty good, because if you look at their saturation performance, they don't have a soft compression, which usually gallium nitride has.
Yeah.
And due to the soft compression of gallium nitride, its P1 dB point is something which is not very much easily realizable, or you can predict. So definitely GaAs and LDMOS are still the candidates for narrowband applications. The unfortunate thing is that 5G requires broadband performance. And we are talking about 100, 200 megahertz channels and even 1 gigahertz channels. So when we talk about that, the impedance performances of LDMOS and GaAs are not that good. However, there's a talk about high voltage LDMOS devices, which will have slightly better impedance performance, but again, not as good as GaN. So I can definitely see that going forward, GaN will be the choice for broadband, high efficiency devices for 5G. How are we going to linearize them? Whether we are going to have circuits which are passive, which again pose a difficulty, because if you go back into GSM time or even 4G LTE, including second harmonic terminations or third harmonic terminations was so easy because those harmonics were out of band of the channel. Whereas if you have a 1 gigahertz bandwidth to operate in, harmonics usually fall within the band. So you can't include your harmonic terminations even. So some sort of external linearity improvement technique will be required. So in short, I think GaN is not going to completely replace everything, but it will be a choice for 5G broadband applications. I think there's no doubt about that.
Another question, please? Okay, if not, we can move to the next presentation given by Diane Perez. He will speak about compact antennas in rich gap waveguide with circular polarization at 60 gigahertz. So, Diane, the floor is yours.
Okay, you can see my screen properly?
Yes.
Yes. Okay. Well, good morning. My name is Diane Perez Quintana. I speak from Public University of Navarra. I will present to you today our investigation entitled Compact Antennas in Rich Gap Waveguide with Circular Polarization and 60 GHz. Well, I will follow the next content. I will do a brief introduction to study the state of art and some question about the state of art in this wave. My presentation is divided in 2 blocks. In the first block, I will speak about the design and simulation and experimental result using using this first feeding system, and after that I explain the other block. The second block is using this feeding system. I will talk about the antenna design and simulation and experiment result. After that, the comparison table. I will analyze a comparison table with our antennas and others, and finally the conclusion of this investigation. Well, the implementation of the 5G mobile and Internet of Things is presently a fact. The high demand for faster speed and the greater volume of information required for this application is impossible to satisfy with traditional operation bands and microwave that don't give appropriate solution. Nowadays, the constant growth of the technology and communication has resulted in saturation of the lower part of the radio frequency spectrum, which is limited resource. Therefore, designing at high frequency rather than a solution is a necessity, and I will have the antennas as fundamental device is a priority. The 5G is expected to include a significant increase in bandwidth with high frequency carriers, high density in connection station, and a large number of antenna in edge communication device. For the reasons, antennas working in wide frequency range, compact and adaptable to any surface with the minimum possible loss is a key objective in this regard. Recently, the 60 GHz frequency band has received interest and attention due to its potential and benefits for many incoming applications. Here, the first question: traditional feeding techniques can solve the new system or can be used in the new system? Well, the answer is not. The big problem with these feeding techniques is the high frequency losses. When the frequency increase, the lambda decrease, and the transmission in this case is the transmission line and the coaxial cable using dielectric. It has a high losses in high frequency, and the waveguide is a good option, but it has great losses too in high frequency due to the electric contact and the other fabrication problems. Recently, the researcher has developed in the last decade a new feeding technique. In this case, the gap waveguide technology developed from the beginning by the Professor Per Simon Kildal and your team. And their team. Develop this feeding technique. It's very easy and it's very easy in the current time. I present you here the three variants: the group gap waveguide, the ridge gap waveguide, and the microstrip gap waveguide. For adaptability, all of them. For adaptability, we use it in our investigation the ridge gap waveguide. All of them has low losses in high frequency and don't need electrical contact between the layers. The losses are very low in comparison with the other feeding techniques analyzed before. Well. Up to this point, the first objective of this investigation is to design antennas able to achieve good radiation characteristics and low losses using the ridge gap waveguide technique. In addition, all designs should be able to support the implementation of 5G mobile communication. Beyond that, it's evident that minimizing path loss is very important in this investigation. This objective can be achieved using circular polarization, but why circular polarization? Well, circular polarization in wireless communication system has several advantages over linear polarization. It does not require polarization alignment between transmitter and receiver and is more robust against multipath effect. Here you can see several examples of antenna arrays using ridge gap waveguide implemented circular polarization with these techniques. Well. In our job, we design in the first block these two antennas. The first one and the main and the principal antenna is the diamond antenna. Here you can see an antenna with one slot in the top layer, and unadapted of this antenna is the diamond hole groove antenna. This antenna is a variation of the first diamond antenna. Well, this antenna is composed for two layers: the principal layer, the radiation layers, and the feeding layer. Each antenna is fed from the bottom here by standard WR15 waveguide to make it compatible with our system, our standard measurement system based on vector network analysis. We feed the antenna for this hole, and we couple the wave using this transition here to couple the wave on the ridge and can fit the two arms. I explain it in the next slide. Well, important things we use in these in these antennas the same feeding system. In this case, both antennas share the same feeding system. Well, analyzing indeed our first feeding system, you can see here the hollow of the WR15 waveguide. We couple the wave using this transition here. It's a simple transition. We implemented three steps, and we couple the wave from this direction here. We analyze it, in simulation the reflection coefficient. You can see here the good matching in all the band. In this case, we're using as central frequency 63.5 gigahertz. The principal parameters are shown in this table. Well, using this feeding system, we can obtain, or we need to generate the circular polarization, and this is the more important section in our investigation. How generate circular polarization? In this case, we implemented in the end of the ridge two orthogonal arms. In this picture, you can see very well. It is a simple, compact way to generate circular polarization. Two orthogonal arms with different length. In this case, need to be lambda over 4 with this different, we can generate circular polarization, and we can rotate the electromagnetic field. In this picture here in the right hand, you can see the electric field distribution and in the central frequency and the rotation of the electric field. In the other picture, the surface currents in the top layer. In the case of the diamond antenna, you can see the rotation of the surface current on top in the top layer, and it validates our design to obtain a circular polarization in a better way. Well, analyzing in depth our first antenna, the diamond antenna, you can see here the manufactured antenna is very nice. Analyzing the simulation result, we obtain a discrimination of polarization, the more than 15 dB. In this case, analyzing the radiation pattern, we obtain a right-hand circular polarization. Analyzing the three variant, we have all the gain in the right-hand circular polarization. Well, in this case, we analyze the experimental result, and we have the coefficient, the reflection coefficient here, and it has a good agreement with the simulation. In the axial ratio plot, you can see here the simulation is much better, but we achieve a good axial ratio. In this case, we obtain more than 6 gigahertz in bandwidth, and put all these results together, we obtain a practical bandwidth around the 10.74%. It means around more than 7 gigahertz of bandwidth. It is a great bandwidth because it is a simple element, very compact antenna. Well, analyzing the discrimination of polarization here, we obtain more than 15 dB, the discrimination between copolar and cross-polar polarization, and a big gain around 6 dB at 67 gigahertz. Well, in this order, we need to we want to improve this gain, and we design the update of this antenna. The diamond hole groove antenna is an optimization, or sorry, an update of the first antenna. We do a cavity here to improve the gain in the design. here we share the same feeding layer. In this order, we have the same circular polarization, in this case, right-hand circular polarization. The discrimination of polarization is similar, more than 50 dB. And analyzing the experimental result, we achieve a good reflection coefficient here. In the axial ratio case, we can see the plot is, the result is much better than the first antenna. You can see that our measurement results are in all the band achieving a maximum bandwidth more than 11 gigahertz. This it means around 18% with respect to the central frequency. Analyzing all the plot together, the practical bandwidth of this antenna is around 15%. It means more than 9 gigahertz in all the band. It is a very important result because we designed a simple element. It is able to achieve more than 9 gigahertz in all the operation band. Well, analyzing the copolar and cross-polar radiation pattern, the discrimination of polarization is more than 15 dB, and the gain is improved too. A peak gain around 11 dB at 67 gigahertz is achieved. In this case, all the band is above of 9 gigahertz. Here you can see all the gain is above of 9 dB. Sorry. Well, up to this point, we implemented two antennas, but we need to approach the physical area in the top plate. Well, in this to this end, we designed the first bull's eyes antenna able to generate circular polarization for itself. In this case, you can see here the top plate is covered with four concentric rings. We using the theoretical liquid wave to increase the gain using the Booley's theory. In this case, we approach all the physical area in the top plate, adjusting the feeding technique because the Booley antenna are a narrow band. We achieve good results. You can see here the port-to-port analysis is is very good. Reflection coefficient. Analyzing the radiation line here, you can see a good picture. The four rings are around the central slot and the feeding layer. Well, in this case, we need to adjust the length between the arms. In this case, doing some simulation, we choose an optimal a good different length is around the lambda over 10, because we create a cavity here to put the four corrugation, and we need to adjust the different lengths between arms. But you can see here the electric field distribution on the top plate. The rotation of the electric field validate the circular polarization achieved. Analyzing all the other parameters, we achieve a good reflection coefficient in good agreement with the simulation, and the axial ratio is very good too. We increase the gain around the 18.4 dB, and in the central frequency, in both cutting planes, we achieve a good discrimination of polarization. Put together all these results, we can summarize that the axial ratio is below of 1 dB in all the band. The gain max, the big gain is around 18.4 dB in the central frequency. In this case, 58.5 gigahertz. Effective area around the 9%, and in this case, the main lobe of beamwidth is equal to 11 degree. Well, In this way, we can do a comparison table. This comparison table of our antenna with similar antenna reported in the literature. Note that the most of these designs are antenna arrays, which are comparatively more complex than our antennas that are based on a single radiating element and a simple feeding network. Certainly, in some case, the antenna mentioned here have larger gain than the ones proposed in this paper. So the bandwidth is restricted, you can see here. But in addition, we present three variants. We present three variants, and sorry. We present three variants that cover very well the requirement for application in millimeter wave band. The D and DHE antenna have a large circular polarization bandwidth, and finally the Bulleye antenna have a narrow band but a high gain around 18.4 dB. I need to say that these three designs are very compact and simple, using in many applications in this band. Well, as a conclusion, we present here three simple, compact, and low-profile antenna using the rich guide technology. We present two novel and simple mechanisms to generate circular polarization. And this is very important due to the high frequency works. The bandwidths are very large, and we achieve a maximum gain of 18.4 dB using the first Bulleye antenna able to generate circular polarization. Thank you very much, and I can respond all your questions.
Okay, thank you, Diane, for this presentation. Now, time for some questions.
I saw a lot of difference between simulated and measured results, particularly for the first antenna. Why so much difference?
Well, yeah, thank you. You see, for example, I can change my slide?
Yeah, yes. Yes,
okay,
please.
Thank you. Well, you maybe you see, for example, here, no?
This one, yeah, some other.
Yes. Yes, this is a very good question, because in this case we need to make our measurement in gain using a linear antenna. A linear antenna. You know, we have a circular polarized antenna, and we need to compose with a linear antenna. In this wave, we have some variation here, because the phase is very difficult to achieve a good variation, because when you compose the linear to circular polarization, the phase need to be a good precision. And if you have some losses or maybe reflection in the measurement setup, you can achieve this variation. But if you can see in the last antenna here, the Bulleye antenna, the measurement are very good, because it has more gain and is much easy. I can see it's more easy to make the measurement.
So you did all the measurements for this CP antenna with LP antenna, right?
Yes.
I mean, gain measurement.
Yes. And
okay.
after that, we composed the both components, vertical and horizontal.
I get it.
Okay.
But you could have done the measurements using rotating dipole, using the not a stationary one as per the standard procedure. In fact, I have got another question. What is so much necessity of circular polarization? Because it's, after all, usually it's done to eliminate the effect of polarization mismatch. But at this frequency range, there's no propagation through plasma, no radial rotation type of thing. So why is it so much necessary?
Sorry, I can't hear you.
Why is the necessity of circular polarization so much?
Oh,
In
yes.
this case?
In this case, yes.
This
Well,
example, yeah.
yes. Well, for this application, you say. Well, the necessity of implementing here circular polarization is because the main of application in 5G or Internet of Things in this frequency, we have a lot of absorption of the in a room, maybe because we have a great transference data rate between transmitter and receiver, and to avoid the multipath effect losses in the signal, we need to try to approach all the advantages given by circular polarization, and you can obtain in all position, whatever position is the receiver, you can obtain the sorry.
Yeah, that's right. You are ensuring reception always, but also you are ensuring minimum 3 dB loss.
Yes,
Isn't it
yeah.
so?
Yes, of course, yes,
Minimum
yes.
3 dB always.
Yes, yes, of course, but 3D, yes.
Okay, okay.
Yes, you are right. Yes, but well, in a small room, and when you have when you design this high frequency, you need 3 dB loss is I think enough, or you can approach all the other component signal. I think.
Okay.
Yes, thank you.
If there's any other question, I am through.
Okay. Is there any other questions, please?
Let me ask you a question. I mean, this antenna business is very interesting. Into my knowledge, Bhaskar Gupta is, of course, Professor Gupta is an expert, the world famous expert in this business. My question, Diane, is very simple. Did you ever try to solve any simple equation before you start making your antenna designs? Or you just select the shape of the antenna, put in the HFSS, and do optimization and come up with the result?
No.
How do you do that?
Yes, no. Below that is a hard work. Yes, of course.
It's very hard work, I know.
Yes, it's very hard work here because yes, you can see here just a group of plot with curve, but we need to design with good precision to obtain the circular polarization, and we need to select very carefully the slots. We need to do a very a deep analysis in the linear in the transmission line using this transition to couple the wave in the reach on the feeding system. And in first of all, the first of all is to design to make the bed of Nile to achieve our frequency band, because these pings, this feeding technique, the Gabber guy, is very strong, but you need to do several very specific calculations to achieve this forbidden band to design this antenna in this way. And yes, maybe we need to do optimization in the last part of the work, but in the first part we need to work very hard to achieve all the principal parameters.
Thank you so much.
Thank you.
Other question, please. Okay.
Okay. Thank
you. Thank you, Diane.
Thank you very much.
Now let's move to the fifth presentation. And this session is given by Alexia Moreno. Alexia, you are with us?
Yes.
Okay, so the floor is yours. Yeah. The floor is yours.
Okay. Thank you. Well, 1 second. Could you hear me?
Yes.
Hello?
Yes.
Okay. Sorry. Well, I'm going. Welcome to the presentation of this work. The work is titled Highly Efficient Ultra-Thin Zigzag Half-Wave Plate Metasurface in Terahertz Range. My name is Alexia, and the co-authors of this paper, of this work, are Sergei Kuznetsov and Miguel Beruete. Well, this is the index. I'm going to start talking about the state of the art. Then I will explain about the design and simulation. I will also show the experimental results, and I will finish with the conclusions. To give some context about our work, I think it's important. It's necessary to highlight the importance of controlling the polarization of electromagnetic waves across the entire spectrum. That's the reason why polarization converters arise. Concretely, in our group, we focus our attention in the terahertz range, which means from 0.1 to 10 terahertz, due to the interesting applications as sensing, imaging, or spectroscopy in this range. The classical or the more common materials using structures using this part of the spectrum are the 2D metamaterials, also known as metasurfaces. The reason is that they are able to control the waves in a sub-wavelength range. So it allowing very good performances as, for example, high efficiencies, compact geometries, or device miniaturization. Well, there are two kinds of polarization converters based on these metasurfaces. One of them is quarter wave plate, and the other one is half wave plate. The first one converts linear to circular polarization, and the second one from circular to the circular cross polarization. This means from right to left and vice versa. There are two operation modes, reflection mode and transmission mode. With the first one, we obtain very high efficiencies in an easier way than with transmission mode. Moreover, we often need bulky structures with transmission mode to obtain high efficiencies. And currently, or until now, the best performances obtained with this in this transmission mode are a maximum transmission efficiency around 80%, with typical thickness of lambda over 3, even lambda over 10 in the best case. Sorry. So this is the challenge of our work, to get more efficiency in this operation mode and using a very thin structure. Well, it's interesting to talk first about some basics, principles or definitions, as for example, complementary surfaces. One complementary surfaces is a surface in which we have lossy metal and also an air hole pattern. And if when we interchange this metal, this spec for with the air holes, we obtain the complementary surface. These kind of surfaces are interesting because they comply with the Babinet principle. The Babinet principle states that you can interchange, you receive the same diffraction electric pattern diagram at the output of this device with one surface and the complementary one, with the only difference of the intensity of the electric field at the output. Well, With this, if we combine these complementary surfaces at the same time, in the same space, we obtain self-complementary surfaces. The more known maybe is the chessboard, as we can see in these pictures, and there are also more. Applying the Babinet principle, combining with the energy conservation theorem, we can obtain this figure, which is extracted from the Babinet thesis, very useful to understand that we have the linear transmission coefficient and the reflection coefficient would be the same. So we can move around these two circumferences. And if every point of this circumference is a frequency point, we can observe that always it's possible to guarantee plus minus 90 degrees of phase difference between linear components for any frequency. And always is possible to find a frequency at which the magnitudes are identical. So these two are the basis to obtain a quarter wave plate. So in this work, they obtain this quarter wave plate with this geometry zigzag, self-complementary metasurface, and they work in microwave range, and they work in transmission mode. They obtain very good performances. The one frequency we can observe in the graphs that the magnitude value is very good, and the phase, also the values of the phase, and the axial ratio is also very near to 0 for one frequential point. So we based our work on this self-complementary surface, but what we want to create is a halfway plate. So what we do is adding a new layer, a new metallic layer. So we have to break this self-complementarity, and we obtain a bilayer metasurface, and we need to make a tuning of the parameters. So we change the zigzag angle and also the width of the metallic strips, obtaining this kind of sandwich of metallic layers, and using in the middle a dielectric substrate. This dielectric is polypropylene, and we obtain a very thin, very good thickness, lower than λ/20. We are working in an operation frequency of 149.25 gigahertz. So also the period, the side of the unit cell that which we are observing now is lower than λ/2. So we can see here the performances. We can observe how is the behavior as halfway plate in transmission mode. In the picture in the left, we see that for the operation frequency, the phase difference is almost perfectly 180 degrees. So we obtain this phase difference is between linear components at the output of the device. So we have a very good behavior. Also remark that the simulation and measurement are very, very similar. Well, also to know how good could be when we need to reject the polarization that we don't want. We define the cross-polar discrimination, which is around 35 degrees, which relates this cross-polar at the output with the copolar at the output. No? So we have this high value, and also this cross-polar discrimination is related to the axial ratio. And we see that there is a very high purity of circular polarization around the operation frequency. Furthermore, we wanted to study this structure because we think that it's an interesting structure. So what we did was test the robustness of this structure and applying a misalignment between both opposite metallic layers in y-axis and in x-axis, as we can see in the pictures. The green, the top layer is the green strips, and the bottom layer in blue. So for this study, what we did was in pink with a vertical polarization with an electric field polarizing in y-axis for both cases, the X-shift case and Y-shift case. What we observe is that the transmission coefficient remains almost in near 0 dB in all the spectrum, and also the phase with a variation of 0.2 or depending on the frequency, but we can reject this variation, or we can it's negligible. I mean, for Y shift, we observe the same behavior with a little variation in frequency, but also negligible. And the more curious case is when we attack with an horizontal polarization, because we observe that again for X-shift case, the values remain unmodified almost for every misalignment step. But for Y-shift, we observe that the transmission coefficient values are good, but there is a frequency blue shift more significant. So in order to understand this behavior, what we did was study the fields between the structure. We made in this cutting plane, we observed the electric field lines, and we see that for X-shift case, along with the increment, the field lines are almost unmodified. So this explains that the behavior is very similar. But in the case of in the Y-shift case, this coupling, this electric coupling, diminishes along with the capacitance. So this is probably, we conclude that this is the reason of this blue shift. Now I explain, this is the setup. We don't have circular polarized antennas here in our lab. So what we did was use two antennas in transmission and reception for elliptical mirrors. And we put the sample in the middle of the wave with two different configurations. The first one, as we can see in the picture in the left, for the electric field polarized in y-axis, we obtain the transmission components and linear components in y-axis and x-axis, and then we rotate the sample and repeat the same process. So applying the matrix transformation from linear to circular, we obtain this transmission matrix. So we can now express the electric field at the output as circular basis, in circular basis. And here we can see finally the experimental results. This picture in the left are the fabricated samples. This is the aligned one. There is always a little error in the alignment between layers, but like the structure is very robust, it's okay. This is the X-shift case, and the third one, the Y-shift case. Okay, so when we see the transmission coefficient, what we did was to take, we observed a very good agreement between simulation and measurement, but we also observed a little difference when we obtain from right to left and from left to right. So that is due to the error phases in the linear polarized coefficient that we obtain when we are taking the measurement, okay, for this matrix. But we appreciate that the efficiency is really good. We achieve a 92% of conversions transmission. And also the cross-polar discrimination remains in the 3 cases around 30 dBs. In the Y-shift case that I mentioned before, we observed that, yes, there is a blue shift in the frequency, but however, it continues working as halfway plate properly. So that's a very good thing. Here are the conclusions. I have presented a robust terahertz halfway plate converter working around 150 gigahertz with a bilayer geometry. The thickness is lambda over 20. We obtain a very high conversion efficiency, around 92%. Which means minus 0.7 dBs, and the cross-polar discrimination is around 30 dBs, and the axial ratio is near to 1. So that's all, and thank you for your attention. If you have any question.
Okay, thanks Alexia for this presentation.
Thank you.
So do we have some questions? I think Professor Gupta has one, maybe.
Okay.
It's not that high. Ask questions all the time. Let the others ask.
Hello?
Yeah. Let the others ask. I have asked too many questions.
Okay. Okay. Sorry?
Professor Elmer, do you have some questions?
Well, it is a beautiful presentation. We really appreciate it. This is out of my area. I understand that it works about 150 gigahertz. She's done a good job. Thank you. Thank you, Alexia.
Thank you.
Good work. Thank you.
That's a really good one. I just want to know, have all the measurement facilities at your place?
Yeah, we take all the measurements were did here in our lab.
Okay. That's good. Meta surfaces are truly very, very interesting. Some of my students, one student is applying meta surface for non-invasive detection of breast cancer detection. I mean, the resonance is getting shifted. And my point is that meta surfaces, have you thought ever of just like providing time-space modulation to meta surfaces? That's, I think, a very new area.
Yes.
Modulated meta surfaces.
No, I didn't. I have never done, but yes, it's an interesting area. I think meta surfaces are every day more. There are more studies and more.
Right.
More changes.
Let me ask you this, Alexia. How do you comment on the nonlinearities of these meta surfaces? I mean, this is obviously meta surface and anisotropic materials, right?
Yes.
Would you comment on that? And does the nonlinearities or non-isotropic behavior of the material creates any problem as far as design is concerned?
What, the design? You mean the design of the
use of the material? I mean, because you're going to be using this. If you cannot control the physical properties of the material, then you can have some problems as far as the application is concerned, whatever the application is going to be.
Well, I don't know if we can maybe by adding more layers, or we can modify some properties of the meta surface. No, I don't know if I answer your question properly. Sorry.
That's all right. I mean,
No, Siddiq has asked a very pertinent question that we have to control the properties. That's why
control the properties of the for controlling the properties. Maybe we can play with the distance between the layers of this bilayer structure, and for in general sorry.
Yes, please, please go on, carry on.
No, but I don't know if in general in meta surfaces, I think it's possible to make this change in the to play with the anisotropy with of the meta surface. I don't know.
That's all right. I mean, you have a long way to go through it, and
yeah, lots of interesting properties are there associated with meta surfaces. They're coming in a big way.
Right. Okay, thank you so much, Alexia. Good work. Congratulations.
Thank you.
Congratulations.
Bye. I stop the screen.
Thanks, Alexia, for this presentation. Now let's move to the seventh presentation given by Mohammed Khamlishi. Mohammed, the floor is yours.
Yes, I'm here, Professor. Good morning, everybody. Thank you for your comment today to see this presentation. It's great to see you all in this video conference. My name is Mohammed Al-Khamlishi. I am PhD student at Microwave and Electronic Group of Al Malik Saad University. Today, I'm going to talk about RFID tag antenna for healthcare applications. So this is the outline of my presentation is as follows. First, I will start with a short introduction to the RFID technology and define the RFID system. Then I will describe the proposed antenna. In third part, I will present and discuss some obtained results, including, for example, reflection coefficient, reading range, and radiation pattern. And finally, I will give you some concluding remarks and introduce our future work. So before starting the discussion of the topic, I will give you the definition of RFID technology. The RFID meaning the radio frequency identification. It's a method to capture the information on an object without using the human to read the data. For example, we place the tag in the object that we want to detect, and in the other side, we place a reader. An RFID system is generally composed of two components, a tag which connected to the object being identified, and the reader which used to read information from a tag. Here we can see some RFID technology application in different areas like a transport network, stock management, and healthcare applications. Low cost and flexible radio frequency identification tag for automatic identification, tracking, and monitoring of blood products is a great demand by the healthcare industry. Robust performance to meet security and traceability requirements in different blood samples, collection and analysis center is also required. So in this presentation, I will give the novel low cost and flexible passive RFID tag for blood sample collections. This is the geometry of my tag. The dimension of the proposed antenna is shown in this table. It's very simple design. It has the area of 15 and 49.5 millimeters. And other dimensions are presented in these tables. It was optimized by using the commercial electromagnetic software CST Studio. The tag consists of two symmetrical pads with the two each dimension their substrate arms. Both pads are separated at the center by means of two different gaps, this gap, and this one, which are placed at the left and the right sides. The IC chip is mounted across the gap S between the two pads, while the gap G is used to introduce the capacitive behavior to the tag antenna. In this figure, the simulated reflection coefficient for different scenarios. For the first one is the tag. The first one is the tag attached to the tube full of the blood, and the tag attached to the empty tube. And the third one is the tag removed from the tube, but maintained in the initial curvature of the tube. And the fifth one, the tag removed from the tube and attached to the blood bag. As we can see in this figure, we have the good impedance matching is obtained in the desired band. It's a European band when the tag is attached to the full tube of the blood. Here we can see this slide is present one of the most popular technique to measure the complex directivity, the electric permittivity of the solid and the liquids is the electromagnetic characterization technique is not destructive and allows to carry out the fast broadband measurement of biological substance. The complex permittivity of the tag antenna substrate, the clinic tube, and the blood were measured between 0.5 and 2 gigahertz by employing the coaxial probe method and vector network analyzer. The results were obtained at the room temperature for tag antenna substrate and for the blood and for the tube. The measured result of the materials involved in the tag design, the real permittivity obtained for the Kapton polyimide in the frequency range from 0.5 to 2 gigahertz is presented in this figure. The result shown the constant real part of the relative permittivity around 3.2, which is a good agreement with the typical manufacturer data 3.1. The imaginary part of the relative permittivity of this material is not given because it has a very small and negliged during the design of the tag antenna. Since the electric losses and the power dissipation in the polyimide substrate will be very small. Also for the tube, the material we found the same datasheet value for the permittivity and the losses tangent as we found in the datasheet. For the blood, this is the measurement permittivity and the conductivity of the blood is similar to the human ones. The real permittivity is around 62 and the conductivity 8 siemens per meter. And to verify some propriety, the fabricated prototype of the proposed tag antenna has been realized using the laser milling machine LPKF proto laser. And this tag is ready to attach it to the blood tube, as we can see in this picture. We can see in this slide the characterization of the tag's antenna impedance. The impedance of the proposed RFID tag antenna was characterized by using two-port network analyzer and the port extension technique. The Impedance of a proposed antenna measured in an anechoic chamber by means of this technique in the frequency range from 0.5 GHz to 2 GHz is shown in this figure. The simulated input impedance of the tag and the impedance of AC chip are also included. Except for this small shift in the resonance frequency, a good agreement between the simulated and the measured result for both real and imaginary parts of the input impedance is obtained. This small mismatch is due to the inaccuracies for fabrication in the lab of the tags and negative mounting and soldering effects. This slide presents another critical parameter that determines the performance of RFID tag antenna is the reading range, which corresponding to the maximum distance at which the RFID reader can detect the modulated backscattering signal and successfully identify the tag. The simulated and the measured reading range obtained for the proposed tag attached to different tube sizes in this is presented in this figure. The measured read range carried out by the means of the anechoic chamber and the tag formos voyantic system. And for the simulated reading range, I use the CST Microwave Studio and the MATLAB to find the results. It can be observed that the measurements are good agreement with the predictions. The measured read range reached the peak of value 2.2 meters at the frequency of 867 megahertz when the tag is attached to the smallest size tube full of blood, while the largest size tube has a peak value of 2.3 meters and 60 megahertz. At the 867 megahertz, the largest sized tube presents a reading range of 2.25 meters, which is similar to the measured value 2.2 for smallest size tube. For both tube sizes, the reading range drastically decreased when the tubes are empty. This confirms that the proposed design can be applied to different tube standards and that it's possible to detect the tag at a reasonable distance when the tube is full of blood. In addition, in both cases, the reading range drastically reduced for the empty tube. This behavior can be used to reduce the amount of information collected in a tracking system coming from the empty tube. To check the performance of the proposed tag attached to the tube full of blood in a natural environment, the measurements out of an anechoic chamber have been realized in two scenarios. The first scenario consists in the measurement of a signal individual tag, while the second one, the measurement of the tag located behind a group of 4 tubes full of blood. This figure depicts the reading range for these two scenarios. As we can see, there is no substantial change in the performance with respect to the previous result obtained for the individual tag by means of the voyantic tag formant system. All the reading range reach the same peak value of 2.2 meters, but shifted to the high frequency of 875 megahertz. On other hand, the results of the second scenario confirm that the group of fillet tube located in the vicinity of the tag does not greatly affect the performance. In this test, the maximum reading range and the resonance frequency slightly decreased to 2.1 meters and the frequency of 870. The radiation diagram shown in this figure, the radiation patterns were obtained for the proposed tag antenna attached to the blood full of the blood at the 867 megahertz by placing the tag in a horizontal or vertical position. The H plane and the plane cuts of the radiation pattern can be measured using the Voyantic tank formulas. As you can see in these figures, the simulated and the measured results are in the good agreement for both A plane and H plane. The radiation patterns are essentially quasi omnidirectional at the frequency of 867 megahertz and with the linear polarization. The maximum radiation in H plane is not directed at the broadside, but it's appear at the 330 degree. In addition to this slit in the pointing angle, we observe that the H plane radiation pattern is asymmetric. This is due to the effect of the feeding point of the antenna and to presence of the blood tubes along the backside direction. In this slide, the study of proposed tag as a sensor to determine the blood level in the tubes proposed in this study is a consequence of the variation of the tag power sensitivity. In addition, how the blood level affects to the reading range is also presented. The aim of this study is to test the proposed tag exhibits good level sensing capability and if this the variation in the blood level can have the impacts on the reading range. The results, the results show in this. The results have been obtained when the volume of the blood inside the clinic tube vary from 4 milliliters full tube to 0 milliliters empty tube. It can be observed that the minimum power required to activate the tag is shifted to high frequency when the volume of the blood is decreased inside the tube. This is the consequence of the capacitive design proposed in this presentation, which increases the sensitivity of the tag to the presence of the blood. This study is completed with the reading range. The reading range gradually decreases at the same frequency, 867, when the volume of the blood inside the tube is decreased. As we can see in the reading range figure, this is due to the shift of the resonance frequency of the tag to the higher values. In addition, the peak value of the reading range increases when the volume of the blood decreases. This because lower quantity of the blood and with the small absorption in the power radiation by the tag. However, due to the shift in frequency, this increase in the reading range occurred at the higher frequencies, out of the frequency band where the RFID system operated. The result in this figure clearly indicates that the designed tag can indeed be used as a sensor to detect the blood level inside the specific clinic tubes. As a conclusion, a novel compact and high performance tag antenna for a blood tubes traceability application working at the European RFID system is presented in this presentation, and the design of the tag is carried out by considering the electrical property of the elements in which it must operate. These elements are blood, the clinic tube, and the substrates employed for the tag manufacturing. The results have demonstrated that the new tag attached to the clinic tube full of blood exhibits the reading range above 2 meters. Moreover, its capacitive design has shown a strong sensitivity with the presence of the blood inside the tube. Therefore, reading range drastically drop when the tube is empty. This property may be interesting for many tracking applications since it's called reduce the amount of information generated from the empty tube. The same property can also be exploited to use the tag as a sensing system to detect and measure the amount of the blood in clinic tubes. This novel proposed tag can be useful for the design of new blood traceability system using an RFID technology. For future work on this research, we'll consider the integration of a sensor to monitor the temperature of the blood. And also, we can use the intermediate absorbing layer between these two elements, the substrate and the tube, could be considered in the future design. This could help to introduce an additional isolation effect between the tag and the blood and reduce absorption of electromagnetic energy. Thank you for listening to my presentation.
Thanks, Mohammed, for this presentation. Now let's, I think, pick up some questions. It seems that Professor Gupta has one, maybe.
Yeah. Thank you, Mohammed. I just wanted to know, why did you choose this particular substrate? It's quite lossy. Tan delta is 0.016. You can very easily get substrates having tan delta 1 order less. This substrate is so lossy, otherwise you could have even got better range, I think. Hello? Could you get me? Why did you choose this substrate?
Because the flexibility of this substrate, we can bend it. The tag is very simple to bend the tag in the curvature of the tube.
But you have a Roger and substrate, specifically Rogers, which has got 1 order less tan delta and which can also be bent, flexible. That too is. I think that is something which should affect your results. So just keep it in mind, please, for your future research. Check whether you can have to do it. And another question is rather more fundamental. You have shown some simulated and measured radiation patterns. Now, radiation patterns are essentially far-field concepts. Am I right? But these tags operate in near field. So what's the significance of these? They essentially operate in near field. Do you get all these in near field? I have seen many people presenting these radiation patterns for RFID tags, but I don't understand the necessity. Can you please?
Mohammed, you can answer the question.
Sorry, Professor?
Radiation pattern is essentially a far field quantity. Whatever you are showing, that should be valid in far field. But RFID tags operate, especially this type of UHF RFID tags at low frequencies, they operate in near field. So is there any use of these figures? I think the distance plot, that is much more useful. But this, I don't know, many people show these, but in my opinion, there's hardly any use of these. Would I make myself clear?
Yes, the question is clear. Mohammed, you can answer the question, please. Okay, is this radiation pattern or radiation read pattern?
This is a radiation pattern.
Yes, but in far field. Radiation pattern is defined in far field, but attacks operate in near field. That's my point. Anyway, yeah, please.
Because in this application we just work in a small reading range. We don't need to the long reading range. So we just work in the near field.
Exactly, that's what I say.
Yeah.
Exactly, that's what I say, and that is why these radiation is meaningless. Why you waste time on this? Better meaning is carried by the reading distance. In the far field, whatever may happen, that is of no concern for the as far as application goes.
Yes, and also in the Voyant tic-tac formos, we can just get the radiation pattern for the small distance, so the near file. And
exactly, near field is in the near field this does not matter. So anyway, let's proceed. Just to give you some food for thought.
Okay, there is another question, please.
I have one question.
Okay.
Why did you use IC in the tag?
The IC?
The first image you saw us.
The IC. You talk about the IC.
Yeah, between the feeding of the.
The IC is the feeding of the tag of the antenna. In the RFID system, we have the RFID system composed of the tag and the reader. This tag is composed of the antenna and the chip. The chip is the feeding of this tag.
So what is the chip? What is its product number, or what's its specialties? I mean, is there any information?
This chip can collect the data from the radar, the signal from the radar.
Yeah, I understand the functionality, but you didn't give any information about the specification of the chip. I mean, brand or the product number.
This is the NXP chip. Has the sensitivity of minus 17 dBm. And also we have the impedance of the chip.
Okay. Oh, and I can add some information. You know that RFID tags are usually used for traceability of object, so the chip can contain some information, okay, related to this object, so we can exchange them with the radar.
Yes, of course.
Is there another question, please? Okay, if not, we can move to the last presentation scheduled today and given by Yunus Akazim. So the floor is yours, Yunus.
Thank you.
So before, Mohammed, can you switch off your mic, please, Mohammed? Okay.
Do you hear me well?
Yeah, yes, we can hear you, yes.
Yes.
Good. Now do you see the screen?
Yes, we can see the screen, yeah.
Good. Good afternoon. Thank you for all. My name is Yunus Akazim, PhD student preparing a co-title of thesis at Technical University of Catalonia and the University of Abdelmalek Saadi Faculty of Science Tétouan, working on human body part functionality monitoring using microwave imaging. This work will concentrate on designing and the validation of the antenna that will be used for human body imaging, and the presentation will be titled Collateral Double Reach Ultra-Wideband Probe for Functional Imaging. I would like first to thank the member of jury as well as the organization committee for the conference, which allows us to develop, enrich, and share the knowledge between all the participants. The presentation is organized as follows. First, we start by expressing some motivations, then we describe the designed antenna, and the third part, we will validate the antenna by target depth detection in order to see the quality of the target. And after that, we will present the result of the designed antenna and finally the conclusion and perspectives. Nowadays, the existing techniques for microwave imaging of a human body part like brain, breast, or arm and legs consist on reconstructing images or in order to detect the target, in this case, tumors. We also have been working on microwave imaging on the brain, the figure on the top, and arm figure on the bottom, using 16-horn antenna. The second step of our work will concentrate on the electrical signals to study functional imaging to be able to monitor the functionality of the human body part by interacting with the natural response of the synapse inside the brain or the microorganism or the human body cells too. For this approach, our interest is to combine between the location of the target and using the ultra-wideband techniques and the interaction with the natural response of the synapse or the microorganism. Here, the modulated scatter techniques will be used to extract the response of objects under test. And we refer to this approach by functional imaging because we are not interested on just reconstructing images, but also to get the functionality of the object under test, like brain or arm or leg. But today we will present the novel probe element that we'll use for functional imaging. Many microwave imaging systems have been developed, which based on dipole antenna, patch antenna, and Vivaldi antenna. But for a good resolution, we need an antenna which is compact, directive, and broadband. And more important, to match the medium in order to reduce the reflection from the medium. The common solution for that is the horn antenna. To have a small antenna profile and easy transition coaxial to the waveguide, we are proposing the double-ridge waveguide antenna as solution for that, where the feeding is based on the aperture-coupled feeding. The feeding is done through the microstrip line, and because of the extra length from the slot to the end is equal lambda/4, which is equivalent to the short circuit, and the wave is propagated inside the waveguide. Here we have two different side view of the designed antenna that is filled with gray-white matter to match the impedance of the object under test, which is in our case, the brain. The designed antenna shows a good impedance matching for the band of interest from 0.5 to 2 GHz, where the reflection coefficient is under -7 dB. This result is for the antenna radiating in the free space. It will improve a lot when it radiates in the front of the brain model. The designed antenna are used in a linear distribution to locate a cylindrical metallic target inside the high permittivity material as shown in the figure. The goal is to see the quality of the antenna to detect the targets, which is the first theoretical study that we are proposing. And we used two antennas because starting to use the 16 antenna in the circular array for functional imaging. So the extracted S parameter in the frequency domain is combined and converted to the time domain using Fourier transformation by this equation. And then we applied the time to distance conversion up. And we divide by 2. Oh, sorry. We divide by 2 because we have the distance is from the antenna to the target and back to the antenna too. So we divide by 2. What is the minimum diameter of the target in order to differentiate between back and front reflected signal? This question comes from the analysis of result when decreasing the diameter of the target from 1 centimeter to 1 millimeter, where the reflected signal from the back and from the front are confused. And the criteria for minimum diameter is needed in function of frequency bandwidth in order to differentiate between the reflected signals. For this reason, we are used a target of diameter 1 millimeter and bandwidth frequency of 15 GHz. As shown in this figure, we have the first response of the short path and the second of the long path. And the goal is to differentiate between the PL and PS. The difference between the PL and PS equals 0.3, which is the perimeter of the target used for the test. This figure presents the scenario of the target depth detection with the meaning of the PL long path and PS short path mentioned previously. To avoid their overlapping, we need to have the time bandwidth smaller than time delay needed to turn around the target, which corresponds to the difference between PL and PS. And finally, we get the criteria for the minimum diameter to differentiate between the PL and PS. If we want to differentiate between PL and PS using the target of 4.5, we need just 3 gigahertz of bandwidth. But if we want to differentiate between them for a target with a diameter of 1 millimeter, we need 15 gigahertz. To validate the criteria founded, we used a 3 gigahertz bandwidth and the target of diameter 1 millimeter, 1 centimeter. In depth, in this case, we used the target of 5 millimeter. And the target is put inside the high permittivity medium in the depth of 8 centimeter away from the antenna. For this figure, we can clearly detect the depth of the target, which is 8 centimeter, like this. After fabricating the antenna, we fabricate the gray-white matter that models the brain using some corn flour, distilled water, and gelatin. And we fill the waveguide with the fabricated material that mimic the brain. The permittivity is measured using the dielectric probe kit N1501A from KaiSite. And the result is for the bandwidth of interest. In this figure, we have the permittivity and the conductivity of the fabricated phantom, where the real part of the permittivity is around 15 and the conductivity is 0.8 at 500 megahertz. And this is the final fabricated antenna filled with the fabricated gray-white matter. The reflection coefficient shows a good impedance matching for the band of interest and also the matching between simulated and the measured result. I want just to mention that these measurements are for the antenna facing the air, not facing the brain, and it will improve a lot when it's facing the brain. The fabricated antenna are used to validate the equation mentioned before to detect the distance between the two ports. In this case, the distance between the two ports is 2 times the width or the length of the waveguide. And where the length of the waveguide is equal to 3.5 centimeter. From the figure of the time to distance conversion, we can clearly detect the distance between them, which is 7 centimeters. As a conclusion, in this work, we present the design and the validation of the double-reach waveguide antenna with the simplicity of transition from coaxial to the waveguide, which respect the impedance matching between the antenna and the medium of radiation to minimize the reflection. And also, we present the necessary bandwidth to differentiate the reflection from the front and from the back of the target. And finally, we validate the designed antenna by detecting the target and the fabricated one by detecting the distance between the two antennas, between the two ports. The upcoming work for the short term is to study the interaction of the synaptic electrical pulse with the ultra-wideband signals used to locate the object. In this case, the synapse, and to extract the response of the switched target with the model, which models the brain synaptic response using the modulated scatter technique, and finally to deal with the real microorganism using the circular array of double-reach antenna. And thank you for your attention.
Okay, thanks, Yunus, for this presentation. Now let's pick up some questions. There is one. Professor Gupta, do you have one?
Let me ask you a quick question. I'm sorry.
Yes.
Okay, how do you do the matching for these structures? How do you, okay, go ahead.
Yeah, the matching of what? Sorry?
We can't hear you.
Matching with the feet.
Yarman, we can hear you. Activate your mic, please.
Okay. You were talking about the matching and the bandwidth of the antenna, right? So
yes.
how do you do the matching? Do you do some measurements and do some calculations, the theory, or you just by trial and error, you try to match the antenna?
Okay, so first, this antenna is designed for the permittivity of the average permittivity of 15, which is the permittivity of brain, because the average permittivity of the brain is around 15. So this material inside the antenna is the same material that mimic the brain, which is around 15. And in this case, we can match the impedance inside the antenna and the impedance of the medium that we are using for detecting the target or for imaging the brain. Is that the question?
Yeah. Thank you. Thank you so much. So you measure the brain permittivity is about 15.
Yes, it's about 15, and we fabricate the phantom, which is this inside, and this is the picture. This material, which is has the permittivity of 15, as you see in this picture. So we use the same material that we want to image inside the antenna.
All right. Thank you so much, Yusuf.
It's okay.
Yunus.
Yeah.
All right. Thank you.
Do you need to
this was for UW radar, right?
What?
This was meant for UWB radar application.
It's for the brain.
For the brain, but please go to your title.
Yes.
The title you have mentioned something like that.
Yes, the functional imaging.
Oh, UWB is the probe. Just
yes, ultra wideband probe.
Functional imaging, right?
Yes.
Right. Sorry, I misspeak.
Okay.
I thought anyway, your probe is UWB. That you have checked with the frequency response, right?
The probe is ultra wideband, yes, and
yes,
the name that I mentioned before is the WDG, which is the double reach waveguide antenna.
Double reach waveguide antenna.
Yes.
And that essentially is your probe, right?
Yes, which is inspired from the horn antenna that we used before for the brain imaging, and we simplified the transition because it's so difficult to do the transition from the coaxial to the waveguide, and we are proposing this method.
But why do you need it to be UWB? Could you not have imaged with a narrow but high sensitivity probe?
Yes, I will.
Narrow band but high sensitivity probe.
As I mentioned here, we are to locate. We are using the ultra wideband radar techniques. So we need ultra wideband because in time domain we need short pulses. So to get this, we need the ultra wideband.
And you use short pulses.
Yes. Tell me.
Right.
What?
But did you go through time domain analysis, simulation, or anything?
Yes, and as I mentioned here, this is the time domain analysis.
Okay.
As you see, when we increase the first result of 3 gigahertz bandwidth, this response was just one, was overlapping. But when increasing the bandwidth, you see that we can differentiate between all of them. That if we use the target of 1 millimeter diameter.
Good. Okay, thank you. Thank you very much.
Okay. Any other questions?
Do you have another questions? We don't hear from Professor Luigi. You stay with us?
Well, it is a very nice work, Yunus. Really.
Thank you, Professor.
I liked it. It's very nice. I also congratulate your advisor as well.
Thank you.
Nice. So you do the electromagnetic imaging, right?
I didn't hear you. What?
I mean, you do electromagnetic imaging. So you use this probe for the electromagnetic imaging of brain.
Yes.
So you can detect the tumorous region location.
Yes, we did some measurement, but it was just simulation. We detect the target inside permittivity that models the brain as saw in this figure, and we did the other test for the arm imaging. As you see, we can detect the 2 bones of the arm with the skulls inside this, which is which you can, that you can detect from here, that you have the arm inside, you have 2 bones.
But just make a short comment, Yunus.
Yeah.
As a matter of fact, the permittivity of brain is 15, but when you talk about the permittivity of breast, Well, what is the permittivity of breast? It's the same, because here I have a team at the Technical University of Istanbul. We do also work with the imaging of breasts and just to detect the cancers. And we have used a very nice Keysight equipment and probes and etc. Special applicators. So is there any difference, much difference between the permittivity of brain and the soft tissues like breast, like muscles and etc.? Oh, and the brain is different, of course, a little bit.
Yes. Just from the experience that because before I was working with the breast, I can tell you that the permittivity is not so different between them. The difference is that the brain has a lot of non-uniform part, like you have a gray matter, white matter, you have a skull. But for the breast, you have only like 3 or 4 layers, but they are symmetric. And that's why a lot of research doesn't work a lot on the brain cancer, on the brain detection, because the brain has non-symmetrical structure.
Right. In the
very,
past,
very heterogeneous.
Yes. I used to work with brain in the past, in the mid 1980s, and just for the microhypothermia to kill the brain tumors. And then we were using special applicators, antennas, directed to penetrate the tumorous area. So this is very nice, neat. Well, anyway, thank you very much. Let me ask you an independent question. This is an irrelevant question. Are you guys located in Spain altogether?
I'm preparing a co-tutor thesis between Spain and Morocco. So sometimes here and sometimes there.
Good. You're close enough. You're just across the strait. Lovely. I'm jealous of you guys. You're having a nice time over there. Good,
I think Spain is like Turkey, so we have the same weather, so same environment, so it's fine.
Mohammed knows it very well. Now you guys know, of course. Next time I hope to host you here in Istanbul too, once again.
So we need to get a visit to us in Morocco.
Sure. Well, of course, I wanted to come this time, but unfortunately, this pandemic just prohibited everything. Well, all right. Thanks a lot once again, Yunus.
Thank you, sir.
So there is another questions. Otherwise, we can.
I have one question.
Okay. Yeah. Go ahead.
When you're sending the electromagnetic waves to tissue, there will be heat, and it might change the permittivity of the tissue, and it might change also the reflection of the antenna. So did you consider the heat and the changes in the permittivity?
Can you ask again?
When you send the electromagnetic waves, the heat of the tissue will rise, and it might change the permittivity. So did you consider, and also it might change the antenna reflection. So there might some need for extra acquisition in antenna matching. So did you consider the heat in your design?
Just one thing, when I show you the result of the fabricated antenna, this is using the fabricated phantom, the fabricated material that mimic the brain. So if I know what you are asking, for me, I'm not working with the temperature detection, because there is like passive and hybrid techniques to detect the tumors, which based on heating the cells. But for my case, no, just using the radar techniques for detection of targets or cells inside the human brain or human breast or something. You know?
No. I try to ask if you start sending waves to tissue, the heat will rise, and the tissue property will be changed. So it might change your S parameters of the antenna. Since you add the tissue, you show this figure, this picture.
Mm-hmm.
You add the tissue in the antenna, right?
Yes.
So there is tissue, the white.
Yes, the white one is.
Yeah. So it will heat because you are sending microwave. So the permittivity of the tissue might change.
The heat will be in the same time that you start imaging? What does you mean?
Excuse me?
Can I take part in the discussion?
Yes.
I think you need not to worry about that, because for imaging, you have to send the electromagnetic signal over small duration of time, small pulses, small duration pulses, whereas considerable change in temperature, considerable heating would occur only if you send the signal for some time. In this example, in this application, there is no such chance. So that will not matter.
Okay. Thank you, sir, for the answer.
Thanks, everybody.
Thank you. Any other question?
Another question? Okay, if not, we can close the session. We would like to thank all the speakers for today and our guests, Professor Gupta, Professor Yarman, Professor Wiji, and others. So, Professor Gupta or Yarman, if you can add some comment or some suggestions before closing this session.
Well, this was very nice. This was an outstanding session. I really appreciated all the students who presented their papers. They are very valuable to all of us. And it looks like that after the session, we're going to be evaluating the papers regarding the Yarman-Carden Award. And unfortunately, these young fellows gave us a very, very tough task, I would say, to make a decision. So I'm really angry with you guys.
I totally agree with Siddiq.
Yeah. So and our chairman is Gupta, the award committee chairman. He's gonna or Osman. You guys have already collected some but now at least we know by heart that just through the presentation what we have listened, what you have done. So I'm very pleased that you guys has produced a lot, and I wish you all the best. Whether you win the award or not doesn't matter. There's always next time for the conference. Yeah. So we're gonna get ready for that. So unfortunately, we have only 3 hours. Next time, I hope this year I can make more money so that I can give more awards and to many students. So how much I say. So I do appreciate all of you guys, all the people from Morocco, and my friend, the chairman, Mohammed. Thanks a lot. Thank you very much. And hope to see you shortly after the evaluation and to announce the results of the competition, Yarman-Carden Awards. Okay, thank you.
Thank you, Professor Yarman. So, Professor Saidi, do you have something to add?
Can you hear me?
Yes, we can hear you perfectly.
I would like to thank all the students for the effort they have put in the research and the paper they have submitted to this context. And by the same occasion, I thank all the jury members. Professor Gupta, hi, Professor Gupta. We didn't meet for a long time. Yeah. So thank you so much for all the effort you also were putting in this competition since a long time. I guess that since the very first edition, a long time ago, when we established this contest and framework of MMS, you were involved in different juries, different editions. Thank you so much. I thank also all the jury members. And I would not forget to thank the support, outstanding support of my friend and colleague, Professor Yarman, who is really very helpful in developing this conference during the last, since the very beginning of it. Thank you so much.
Okay, thank you, Professor Mohammed, for these words. Now I think we can take a break of 30 minutes, and then we will come back for closing ceremony, in which we will announce the winners for our Yarman Carlin contest, student contest, and also we will announce the 2021 conference, okay, the venue of 2021. Okay, so stay with us.
Okay, thank you.
Thank you. Meantime, I will ask Professor Gupta if we can study the papers, the presentation, and prepare for us the list of winners. Okay?
Just one thing. I think, as per my opinion, all the presentations and all the papers were so good. I really do not want to differentiate this year.
Okay.
You people please decide.
Okay, so we will make a special discussion with Professor Yarman, with you, and taking into account the other comments from other members of the commission.
Yes.
Okay, thank you.
And I just say one more thing only. Although all these papers were so nice, if you just want to find out at least the best one amongst them, that was the last one on that deep probe imaging.
Okay.
Probe for deep imaging. That was even then the best among best. I would say.
Osman, let me ask you: are we okay? Now we have just one guy here. Can we get together among the committee members?
Professor Yarman.
Yes, sir. We should have a special meeting among us with Mohammed and Gupta,
I will,
so that we can discuss.
So how do you suggest we can proceed?
I mean, if there is no student here, but I see Yunus is here now.
Okay, so Yunus, you can lift
so
us.
He just left. Okay, he just left. So we are left among us, I guess. All right.
So just give me 1 minute, please. Okay.
Sure, of course. And we have received. Where is Typhoon? Typhoon is not here, I guess.
So I will ask Yusuf.
Yusuf is here, right?
Yeah.
Professor Yusuf is here. Mohammed is here.
Yeah.
And we have our friend from Cyprus, Typhoon, Simoli. We should ask Typhoon to be back. Maybe then we can.
So we need to wait 1 minute because I am speaking with Professor Zaz in order to make for us some privacy to discuss the the evaluation of all the papers that presented for today. Okay, I also have get some evaluation from okay. So,
Othman, we have a list, Excel sheet, as you know.
Yeah.
And we all entered our scores in there.
Mm-hmm.
If you can put that sheet on the screen.
Okay.
If you share your screen, then we can discuss on that screen as you wish.
Okay, I will screen. Okay, I will share my screen. Okay. So
the last scores were sent by Typhoon.
Okay. Now, yes, this one. Okay. Typhoon. Okay.
But I did not have any such score sheet, and I really did not prepare anything on my own too.
Yeah, okay.
But
So,
I have got all those in mind. Whatever.
Yeah. Okay, that's.
Bhaskar, you don't need any sheet. Your brain is good enough for everything. My dear friend.
Well, learn from you only. Learn from you only.
Oh my goodness. Bhaskar, we have finished one big project in India. The Atal tunnels, the Rohtang tunnels. You remember we were together first time and this was a big success.
Yeah.
We were on the press in India for a good period of time.
National Highway Project.
Yes, that was
that one. Plaza.
Yeah. That is finished. It is the longest tunnel at the top of Himalayas.
Great. Yeah.
After the pandemic,
we can't meet because of this COVID restriction.
Yes.
We have met for a long time, but otherwise, things are rolling on.
Thanks to our friend Mohammed that he puts us together,
You're welcome, Sadiq. It's a pleasure.
I'm still gonna come to Morocco.
Yeah. I see waiting. You remember that we talked about possible collaboration with similar project here in Morocco.
Yes,
absolutely.
We should. I'll come soon, right after the pandemic.
Yeah.
Exactly. After a few more months, let's say.
That's true. So things are getting better in India, Bhaskar.
Yeah, it's much better now.
Would you imagine that we have completed more than $100 million worth of projects in India over the last 10 years? This is incredible.
Yeah, that's
exactly. We've been in India since last 10 years, and we've done a lot. This is great. We completed another project nearby Morocco, Algeria. It's another $40 million worth of a project. But this was 2 years ago. I hope we can stop by. I'm gonna come.
Yeah, absolutely, you should. Yeah.
That's lovely. So Osman, you're in Spain or in Morocco?
No, I am in Morocco. I'm in Tétouan right now.
Nice.
With this situation, it's difficult to move to outside.
That's true.
It's a little complicated.
Yeah.
So, okay. So, do you see my screen now? Yet?
No, not yet. Can you share the screen?
Okay. I will. Share. Now it's okay.
Yes, it's.
We see it, but it's very small. If you can magnify it a little bit.
Yeah. Can you? Yeah, sure.
Okay. Okay. Now it's okay.
A little more.
I magnify a little bit more, a little bit more.
More. Good. Yeah.
Nice. At least I can see now.
Nice. Yeah. That.
Okay.
I see 9 is the highest score. Paper number 3.
9 is the highest score. Paper number 3. Yes.
Which one? Paper number 3.
Number 3. Okay. So number 3 is.
Should be taken an average. I don't know. Actually, we
that's what I would suggest. Yeah. Uthman, if you can just compute the average of
Yeah. First you complete the average.
Yeah.
Okay. So.
Some divided by 5.
Okay, so for each one.
For each one, yes.
For each one, yeah.
Okay.
But we set up this hour together with Mohammed.
That was only evaluation.
Divided by 5, yeah.
Sorry.
By 5.
Every I've evaluated matrix.
Can I put a dollar sign maybe at the beginning?
Okay. Yeah. So we need to switch to French. No, to French.
8.4 for the first paper.
Then you have it down. Yes.
Yeah, they just draw it down.
And then you can rank it. You can rank it also. It's possible to rank and.
Okay.
Exactly. From here you can rank.
Okay. So give me 1 minute.
7.5, 9, 8, 9, 8, 8.4, 9.4.
Okay, now, okay, just...
So although I didn't have any paper, I made the last one first,
okay.
and we did that.
Okay,
but the last one is wrong, I guess. I mean, like we have like 8, 8, 8, 7.58, and 7.5, and the final grade is 9.4. There's something wrong with that.
So no, I think the highest is 9.4. So the highest is okay.
Oh, I see.
Yeah.
9.4.
So if I may, so this is the equation that I have used. I don't know. Yeah, something is wrong. Okay.
Yeah,
so,
8, 8, 8, 7.5. It must be wrong.
It may have some. It may have the paper numbers as well.
Yeah.
You should.
Somewhere it's wrong.
Maybe. Yeah. Okay. Just have it just
add the
1 minute.
Up,
okay.
5. Add the 5 scores and divide by 5.
Take your time, Uthman.
Okay. d'accord. شكرا حافظ شكرا. We are not in privacy. I don't know why. Okay, so just give me 1 minute because other people
Take
can.
your time.
Okay.
Sure, no problem.
No, because other people can, I think, can see us. I don't know why. Okay, I ask. Okay, so.
There are only Tibor with us. Tibor, I think.
Okay.
Oh, is Tibor there? Oh,
Salvatore Corsi is also with us.
Corsi.
Yeah.
Hi, Salvatore.
Hi, Salvatore. How are you? Good to hear from you,
everybody.
Salvatore.
Tibor is also with us. Yeah.
Tibor.
Okay, so
okay, now this sounds. It looks better.
Yeah.
Okay, Osman.
Now it's, I think.
He said something still wrong.
Yeah. No, but don't worry. I will do it.
Should I do this in English?
Now it's okay. So I don't know what's wrong with this, but wait, let's see. So we have to. Fortunately, we don't have many papers. Okay, so we need to divide by 5. Okay, so
by 5.
Yeah, I don't know. So okay, so we need to divide by 5. The same here. Okay, some. The last one says, I think it is.
Okay, Osman, let me just warn you. Our broadcast is still on. on the YouTube. So one of my PhD students warned me.
Okay.
We are there now.
Okay, I will ask Yusuf to stop broadcasting from YouTube. Okay. Sorry for this mistake. Because
but this is also transparent process.
This is a transparent process. I have nothing to say.
broadcast على YouTube وفيسبوك.
It should not be transparent to the